and it's screened. Okay, so
Yeah,
you
cool.
can go ahead.
Cool. Okay, so let's get started. Very most important thing you will hear today, all the files you need for making the workshop work, they are on Discord. So there's a zip file on Discord. Download that one because otherwise it's gonna be really tricky to follow along. Yeah, let me also download the same file. Yeah, and here yeah, I'll open this in documents. Here the Conda environment is managed through the WSL. So this is the Windows subsystem for Linux. So we will have to do some tricks to access our files, but in principle on the computers here, the environment should be set up. For those who are at home, I posted some instructions on how to build that environment. It should work out of the box, but you may have to be a little bit patient because it needs to grab a bunch of packages, and depending on your internet connection, it can really take a while to have all of these. Okay, so let's open up the WSL. So I'm gonna type in here WSL. You see the little Linux penguin there, and that should give you a Linux terminal, and an Ubuntu shell. Um, Okay, cool. That seems to work. So now what we need to do is somehow point it to this folder that we downloaded. And this is already the first tricky thing. So within the WSL, if you want to access, let's say, your Windows drive, you have to go to this mount folder. So you can see here how I type it in, current directory /mnt/c. And that's the C drive of this computer. And in there, then the way the file system is organized is exactly the same as in Windows. So most likely what I'll now have to do is have a look inside of users, student, or something like this. Let's have a look. What's in there? Yeah, users. Yeah, which user am I? Student, I think. And now let's see if I have it in my documents. Permission denied. So I guess I'm a different account. Yeah, let's have a look here. Oh, yeah, I see. Sorry, I am teacher, but probably you are student. So in your case, the user will be called student. In my case, the user is called teacher. Okay, I see. Yeah. Okay, let's do it this way. And now documents. Yeah, and now I can see those files in there. Yeah, and I see here 9add underscore qsar.zip. So you can unzip that on the Windows side, but yeah, I'll try to do it on here. I don't know if the unzip tool is installed or not. Yeah, it seems to work. So now I can go to that folder and let's see. Yeah, all that stuff. All that stuff is in there. Yeah, yeah, try to navigate there, make sure all that stuff is unzipped, and then we can activate the environment and open up the notebooks. Mhm. Oh, yeah, the whole terminal, you mean? Yeah, definitely. Although the size of the text is, well, maybe I can zoom like this. Okay, yeah. Yep. Yeah, so if anyone has any struggles navigating to the right folder, please let me know and I'll be happy to troubleshoot. Okay, so now let's activate the Conda environment. So currently you can see we are here in the base environment and there is a special Conda environment for this session. It's going to be called something like 9add or 9add QSAR. I don't know exactly which one, so I will try something. Let's see if it will work. Conda activate 9add QSAR. Maybe it will work. Yeah, it could not find this environment, so let's list what we have installed like this. And oh, okay. Actually, it turns out that the environment is not installed on this computer. It's only installed on your computers. Okay, so that's great. So you have a lot of time to activate your own environment because I will have to install it here. So let's do that. So I'm gonna create a new Conda environment. I'll call it 9ADD QSAR, and I'll grab it from Conda Forge, and I'll specify that it should be Python 3.12. Let's begin with doing that. Yeah, and it's Conda, so sometimes it can be quite slow as it resolves various dependency problems. Yeah, and I'll have a look here how to build that environment, what I'll put in there. Okay, so the environment is solved. I will proceed. Okay. Okay, so now I have a fresh Python environment. I'm gonna activate it and install some software in there. Conda activate 9ADD QSAR. And yeah, I'm gonna install basically everything in there at once with pip because it's a little bit faster. And yeah, and what we have on there is enough and there are no conflicts. So let's try this. 2.2, I guess. 0.0 light GBM. I'm gonna put in there Node-RED, DQDM, and SciPy, scikit, learn, and pandas, numpy, shep, and Jupyter Lab. Okay, let's see if that will work or if I made any typos, because it somehow, yeah, it looks okay.
Now.
So pip seems to be quite slow on this device, so thank you for your patience. I'll just have to wait until it installs, or maybe I'll kill it and install it through Conda. But usually Conda is even slower than pip, so let's wait. Let's wait for it. Okay, so while waiting for the first environment to install, I'm building a second one so that at least one of the two will work. Just a simple RDKit environment. So let's see if Conda can solve it better than the broken pip here. Because anyway, to start with, I'll have to show around a bit how does JupyterLab work, how does RDKit work, how do certain basic Python things work, how do you deal with molecules in Python. Basically, absolute basics. Okay, so as it's taking endless time to install those environments, I am going to parasitize upon someone else's environment, and I see the de novo environment. It works nicely here. It has JupyterLab installed. So for demonstration, I'll use this one, but again, your local environment, it should just straight up work. So now I'm starting a Jupyter server, which I simply run by typing Jupyter space lab in the command line here. Because this is a WSL, it's not automatically going to launch in the browser, so there's going to be a link here. You can copy that link and open it in your favorite browser. So let me try to open this here in Chrome, and let's see if that will work. Yeah. So now I have a notebook. I have a notebook available here. Yeah, great. So it means that while these environments are building, I can at least demonstrate some stuff. Cool. Okay, so let's start a new notebook, and we can basically pick which kernel to use. So let's use this one, and let's see if this thing has RDKit installed. So yeah, let's try this here. Yeah, it's importing, and great news, it does have RDKit installed. Okay, cool. So who in this room is familiar with RDKit? Can you raise your hand if you're familiar with ArcGIS? Okay, great. So it seems not everyone, but many people are familiar with ArcGIS. So for those who don't yet know it or don't yet know it so well, let me briefly describe to you what it is. So it's a Python library that does basically almost anything you want to do with molecules. It's a cheminformatics package, so it offers a nice way to parse molecules, read smiles, turn them into graph-like objects and do all kinds of things with them, like generating conformations, calculating fingerprints, calculating other properties, managing them in whatever way that you want. So what's the way that's usually done? One typical way to insert a molecule into ArcGIS, so this means to turn it into an ArcGIS mol object, is by providing it as smiles. So that's a line notation for a molecule. Monday it was explained, so let me give you an example of this. Let's pick a molecule. Let's draw the smiles for let's say amphetamine. So let's say I'm gonna do here mol equals, and then here I use this method from chem mol from smiles, and I provide the smile string in there. And for amphetamine, that's gonna be, first there is a benzene ring, so aromatic carbon, ring opening, 5 more aromatic carbons and ring closing. Then there is the aliphatic part, so that's uppercase. In there, there's a branching, and here I put my amine in there. And now inside of this mol thing here, I should have an ArcGIS mol object. Yeah, let's have a look if I can display this. It somehow got stuck with this. That's a little bit strange. Oh yeah, okay, yeah. So here it is. If I put display around that object, it's gonna draw me a nice picture of that molecule. And of course, if I change up the smiles, let's say I wanna decorate my ring a little bit. So let's say I add a second ring on there. I can do that like this. So I open another ring, I close another ring. Yeah, and now we have this nice benzodioxole on there. That's the simplest way to get a molecule into ArcGIS. In practice, if you have large data sets, you will store them in a few common formats. Can be CSV with smiles in there, or it can be an SDF with mol blocks in there. And these mol blocks basically give the connectivity and allow you to give all kinds of both atomic properties as well as molecular properties. Like for example, if you have 3D coordinates, you can provide those in there. If you have some custom properties, you can provide them. You can provide them as fields in there. Okay, let's have a look how my environments are doing. Oh, cool! Actually, it seems like it installed. Uh, Great news. So it silently did that. So let me switch to the proper notebook then. Yeah, awesome. So I'm gonna conda activate 9ADD QSAR, and then finally I should have an environment with all that stuff installed in there. Now I'm currently also already in the right folder, so I should be able to run all these notebooks. Now, first before I do that, let me kill this notebook here, in case it's gonna open the Jupyter on the same port. So now I kill that, and I will activate a new Jupyter server here, and let's see if that works. Yeah, it did. Let me copy that link here, and yeah, so you can see I killed the server, so I have server connection error, and now if I put in the new link, yeah, okay, so and you can see here as well that the notebooks are here. So let's basically this workshop has two parts. The first part is we are going to do something like as simple as possible virtual screen. So I provided some bioactivity data, and we will build basically a simple QSAR model to classify actives versus non-actives, and then apply it on a larger data set and kind of intuitively judge is it fishing out like nice actives or not? That is particularly one to pay attention to because I think it's going to be quite directly useful for tomorrow's challenge. The second thing is a little bit more systematic and broad. Well, it's called here ADME screen, but it's basically I'm predicting blood-brain barrier penetration using various different methods and comparing them with each other. So random forests, gradient boosted trees, rich models, ChemProp models, various descriptors, and so on. But let's first begin with the basic case. Yeah, so I'll open up this one here, and actually this notebook, in principle, it should straight up run like that. There is more or less nothing needed there. But maybe let's say for didactic reasons, let's construct this from the ground up, and I'll comment a little bit what I'm doing as I'm constructing it. So I'm gonna make a new notebook. Yeah. Okay, sure. Like this? Is it better? Yeah. Yeah. You are far off. Sorry. Yeah, and maybe I could remove this. Yeah. Okay. Yeah. So there's a little bit more space. Okay. So we will construct it from the ground up. So let's begin with loading our data. And for loading our data, we are gonna use pandas. So we import it as follows: import pandas as PD, and now this will allow us to open up the CSVs that we have in the data folder. So let's see if that works. We use the read CSV function for that. Then we provide the path, which is going to be something like data slash, yeah, drd3actives.isn. So this is a space separated file with some molecules that are active at the dopamine 3 receptor. And I remember that it's a space separated file, not a comma separated file, so I have to provide a delimiter. And I'm gonna call this data frame actives. So let's see if that works. And that worked. And let's see what's in there. Yeah. So so you can see first you have the smiles, then you have some ID number, then you have the assay type, then you have what the measured value was, you have the units, you have the target, and so on. Actually, as it happens to be, we know that they are actives, so we are only interested in the smiles. That's all we want to grab there. Also, what you can see is that this file doesn't have a header. So we can provide here that the header equals none. Yeah, and now if we reload it, you can see now the headers just became numbered. Okay, so we can do the same thing for the inactives now. And I'll just copy paste this line and turn this into inactives like this. And also go to the file with the inactives in there, and that should be, oh, I cannot find the file, so maybe it's called decoys, actually. Now I remember. Yeah, so it's a subtle difference, but in principle, a decoy is assumed to be inactive. It's not known to be inactive. That's why they're called decoys, not inactives. But they are property match. Okay, let's see what's in there. If that has the same form. Yeah, so here in this case, of course, there is nothing measured. There are no assays measured, so we have just two lines. The ID of the molecule as well as the smiles. Also, what you see in here, we have 34,000 inactives, so we have an imbalanced data set. Of course, we have much more inactives than we have actives because to be active is a bit of an unusual situation. Okay, now we should convert all of these into RDKit molecules. So we just grab the column, we iterate through it, and we use the RDKit machinery for that. So let's import RDKit and let's do that. So like before, from RDKit, we import CHEM, and now we can do list comprehension to do this. So let's call this moles for molecules, actives, and let's write that. So for every smiles in there, we are going to do chem.mol from smiles of the smiles, for smiles in every smiles that's in the first column, like this. Now, because these are 2000 molecules, it may take some time to parse them. Well, this will be quite fast, but those 35,000, maybe it will take some seconds. So for this reason, I'm gonna add a progress bar in there so that I can see how long it will take. So I'm gonna import tqdm, for getting this progress bar. And I'm just gonna wrap this TQDM around the array I am iterating through. TQDM dot TQDM. Okay, let's see if this works. Yeah, so it works, and actually it's quite fast. So now that it works, let's do it also on the inactives. And we just have to change these two things here. Yeah, and as you can see, yeah, even the inactives, it's quite fast. It takes just 10 seconds. Okay, so this is great. Now we have our molecules in our dkit native representation. Now, if we would want to do a bit of machine learning with this, we need two things. The first thing is our endpoints, and the second thing is our features. The endpoints is very easy because we know we have a certain amount of actives and we know we have a certain amount of inactives. So this is just going to be a long array with 2,000 ones in there and 35,000 zeros in there. So let's construct that. Y equals, and let's say the positive category we will call 1, or maybe doesn't have to be a string. We will call it 1. It occurs however long is mole actives, and then we append to this 0 times the amount of inactives that we have, like this. Oh yeah, moles it should be. Okay. Yeah, like this. And now actually you'll see this Y is just like a huge array filled with a bunch of ones and zeros. Okay, so now already actually we have an endpoint. That was very easy, but our features it's a little bit more tricky. So we should calculate some kind of fingerprint or some kind of other descriptors. And I know for this task, Morgan fingerprints work extremely well. So let's calculate those. So how shall we calculate molecular fingerprint? Again, we use some RDKit machinery for it that we have to import. So from RDKit-chem, I'm gonna import the RD fingerprint generator like this. RD fingerprint generator. And now I'm gonna instantiate a fingerprint generator object for Morgan fingerprints. And I'll call it MFP gen, or M standing for Morgan. So that's from this fingerprint generator, I use get Morgan generator, something like this. Yeah, here. Also here already I can specify which settings I want to have. I know for this task actually it's not crucial, so let's use the most basic settings. So radius equals 2 and FP size equals 1024. I'm pretty sure that if you don't specify this, it's gonna pick these settings anyway. Now we can use this generator for calculating our fingerprints directly. So let's call this X because the convention is to put your features in an array called X. And again, we can do a list comprehension. So for every molecule in the both are actives and inactives. So let me concatenate this. We will calculate the fingerprint, and we use the MFP gen for it. MFP gen dot get fingerprint, and I'm gonna make it give the fingerprint as a NumPy array because the scikit-learn estimators we will use to train the models are expecting arrays of this type. Yeah, like this. Again, I'm gonna wrap this in a TQDM just so that we can see how long it will take. Shouldn't be so fast. Should be a few seconds, but still, just to be sure, let's put it there. Yeah, so effectively it's fast. It took 2 seconds. And actually now we have everything in hand already for training our first model. So now let's try that. And what we can do is let's build a LGBM classifier, so a light gradient boosting classifier. And the reason why we will use this one is because it happens to be very robust and it happens to be very fast. So we won't have to wait for 5 minutes while the model is fitting, even if your local computer may be a bit on the slower side. So let's import the LGBM classifier. So from light GBM import, I think it's LGBM classifier, yeah, like this. Let's instantiate it. So I'll call this CLF, short for classifier. And I don't think we even need to change the basic settings. I'm just gonna make sure it will utilize all the cores, and I'm gonna make sure it's not verbose and it's not gonna print out too much stuff that I don't want to hear about. Now, before we fit our model, only one more thing is missing, and this is splitting our data. Because we want to calculate validation metrics, here in this case, it will be just on a basic random split, just to see more or less ballpark how well our models are performing. So let's make use of the sklearn machinery to split up the data. So I'm gonna import that from sklearn model selection, import train test split. Yeah. And yeah, and this is gonna I think this is the order, if I'm not mistaken. Actually, I'll need to have I should have a quick look here. Yeah, it's X first, Y second. Okay. Yeah. Like this. Y test equals train test split, and it's basically gonna shuffle around the data set for us and divide it into randomly into what's going to be our external test and what we will be fitting our LGBM classifier to. So we give it X and Y, and then we should be giving it the ratio of what's in test and what's in train. How is this like called? Yeah, test size is called. Yeah, and let's look it to be deterministic here. Yeah. Okay. And now finally we can fit. And fitting, it's the most easy part. So we have our classifier object and we do clf.fit. We fit it on our train data, so X train and Y train. And now we wait. As you can see, LGBM is fast, so we wait literally for a second. Now we want to see how good our model is. And our model is I would say it's expected to be good, but okay, yeah, let's see. It's a classification model, so we should think of some good classification metrics. Most typical for classification problem is AUC or Matthews correlation coefficient. So let's begin with Matthews correlation coefficient. So let's import that from sklearn metrics. We can import Matthews correlation coefficient. And now what we do is we use our fitted model and we predict the labels. So we do that on X test. So that's the test split of our features, or the features from our test split rather, and we are gonna call this Y predicted. We know what it should be, and that's the values that are in Y test. So now we can print, let's say, MCC equals, and then we calculate this value here. So, and we compare Y test with Y pred. And yeah, so it turns out our model performs well, perhaps even suspiciously well, because MCC is basically bounded between 0 and 1, or yeah, it's bounded between 0 and 1, 1 being basically a perfect correlation. So it means that apparently our task is quite easy. Our actives are really distinct from our inactives. So let's see if the other metrics also trail this. So let's try to calculate the AUC. So I'll import the ROC AUC score. And I'll print out that one. Now, for this, actually, we need prediction probabilities. Because with this Prediction function, we just get the labels, 1 or 0, active or inactive. But if you want to see how well we are ranking and ordering our compounds to see, for example, if we have something like early enrichment, which is very important in virtual screening, we need those probabilities so that we can rank them. So let's get those probabilities. And again, it's very easy to get them. Instead of predict, we just do predict underscore proba for probability. And yeah, and now let's calculate our AUC. So I'll copy paste that here. And yeah, now here instead we should put the probabilities. Now here there is something which is a little bit tricky. This output, it will contain the probabilities for all classes, and we are interested in the positive class. So let's slice that in such a way that we only get that one like this. And now it should give us the AUC. So let's try. Yeah, and so here again we can see that actually this AUC hits the theoretical limit. In other words, our classification problem is probably too easy, or our classifier is very, very powerful. Now, we have a fitted model in hand, so now we can do something with it. And what I suggest to do with it is I have in the data folder a list of smiles of 125,000 commercially available compounds. We can screen those, and then we can have a look. Do those compounds, do they look interesting? Do they look like dopamine 3 binders, or do they just look like random molecules that are false positives? So let's get these molecules into our dikit. So again, we will use pandas for it. So I'm going to call this df zinc because this database is called zinc. It's just a subset of zinc. And yeah, I'm going to use pandas for this. So read CSV. And it's data slash, yeah, zinc 125K because it's 125,000 of them. And yeah, I am not sure what is the separator in this file. So let's have a look. Yeah, it's apparently space separated as well. So let's put the delimiter to space like this. Yeah. And yeah, so you have basically the smiles in there, and then you have the internal code inside of the zinc database. Again, at the moment, we are just interested in the smiles. So let's just grab those smiles. And let's turn them into molecules. So we can call it zinc moles, and we do it in exactly the same way. Mole from smiles for every smiles that's inside of that column. df zinc smiles like this. Okay. Yeah, and this definitely we are gonna make a progress bar again because 125,000 molecules, this will take a little bit of time. Yeah. Okay, it's loading them. And now before we put those into our model, we need only one more thing, and this is converting them into fingerprints. So and with the molecules, of course, it's easy. So let's call this zinc FPS. And yeah, we can even copy paste what we have up here and just change the name of the array that we are iterating through. So this thing here, we just change to zinc moles. Let's see, zinc moles. And yeah, so let's generate them. Yeah, it's faster to generate the fingerprints than it is to read in the molecules because it doesn't have to do any sanitization or anything like this. So it's like super fast algorithm. Okay, so we have our fingerprints. We can use our model. So let's predict the probabilities, and let's put those 125,000 molecules in there. Yeah, so let's call this zinc proba, and let's see how long that takes. Yeah, so it's very fast. It takes something like half a second, and now we have the probability of being active for every single compound in there. So now let's find the most active compounds, and what we can use for that is some NumPy sorting to get the let's say argument that corresponds to the highest value. So let's yeah, import NumPy as NP, and now we can do NP arg sort, so argument sort, zinc probabilities. And again, we are interested in the positive class. So we slice it like this. And here in this case, it's gonna sort from low to high, but we want to have it sorted from high to low. So we can make the array backwards. And let's say we are interested maybe in the, let's say in the best 10. So let's do it that way. So let's take just the first 10 in this line. Let's see if that works. Yeah, so now we have 10 IDs. So now let's have a look at those molecules. So let's iterate through them and let's display them. So from the zinc moles array, we get our best molecules. And then let's kind of intuitively judge what we think of those molecules. Okay, so here they are. Here are the best molecules. And let's say those who are familiar with aminergic GPCRs, they will immediately say, okay, there is very typical, recognizable common motif in there. And that common motif is piperazines, including N-aryl piperazines. Also, what is very typical for these D2, D3, and so on binders is on one side they have a piperazine, then they have a long flexible tail in the middle, and then they have some aromatic thing dangling on the other side. For example, this molecule I'm circling here with my cursor, that's an example of such a molecule. But otherwise, yeah, you can see all these typical motifs are here. Yeah, actually, even here, there's isoquinoline. That's another one of these like typical common motifs. So I would say, looking at these best 10 molecules, I would say our model learned something very shallow. It learned some very kind of like straightforward substructural patterns of what happens to be active and what happens to be measured at the D3 receptor, but well, it works and it gives optimal metrics. So that's the short virtual screen. Okay, so here now I basically built it on the spot, so it's a little bit messy, but here in this other notebook called virtual screen underscore LGBM, I do exactly the same thing. So basically what I was just describing, it's all in there except a bit cleaned away, and there are a little bit extra metrics on there. So let me run those cells and just a little bit comment on it. So yeah, here for example, I add one extra function in there, and this function is the enrichment vector. And in a virtual screening setting, this is actually a very informative metric because if we are virtual screening, typically we'll have a look at millions of molecules and we are interested in maybe the best 100 or the best 200 because we can buy those and the rest we will not buy and we will not test them. So we don't care if we are classifying inactives correctly or if you are having some false negatives. We just care about the fact that in the 150 whatever molecules that we consider the best, that there are as many hits as possible. And the way to quantify this is through the enrichment factor, which is the ratio of the percentage of hits in the subset from screening versus the hit rate in the total set. Yeah, and I just wrote a little function for that. Now here you can see we are loading up that stuff in exactly the same way. Maybe I named the variables in a little bit different way, but it's exactly the same thing. It's just all inside of this one cell. Yeah, here there are no progress bars, so we will just have to wait for a few seconds and hope that it will finish. But so it already finished, so that's not so bad. And again, here we use this light GBM classifier. Actually, in principle, this task it could work with almost any other classifier. One thing you just have to consider is that we have a relatively large data set. So we have something like 40,000 molecules or 37,000 molecules, and already at this size, some estimators like random forest, they will be like a little bit slower. Maybe you'll have to wait for a few minutes or something like this. Whereas this light GBM, it's really well optimized and it tends to find a good solution in a short time. Okay, so let's run this one here, and yeah, you can see that the metrics they follow what we had before. Here they're just rounded up, and also our extra metric that we introduced the enrichment factor at 1%, you can see it's 17-fold. And that's actually the theoretical maximum you can have at this 1%. So in other words, we can say for virtual screening purpose, this is a model that at least within its domain works very, very well. Now, the whole time I'm commenting like, yeah, maybe the task it's a little bit too easy. Because the metrics are so good. So I inserted here a baseline method. And this is a KNN with K equals 1. So basically, it looks for the most similar compound in the dataset, and it just takes the label from that one. So it's like strict similarity-based classification. It's not pooling various neighbors. It's really just only using the closest neighbor. This one actually, it takes a little bit, it takes somewhat longer, although here also it completed quite fast. And you can see the metrics are still like very, very good. If you compare them with the LGBM ones, they're slightly worse, but really not that much worse. So this further confirms, yes, it's really a very easy classification task. This is in part why nowadays people are saying when you are training QSAR models, when you are developing new methods, DUD, which is where these molecules come from, is not a good set to do it because the tasks actually are too easy. One more way to show that the tasks are really easy is by reducing information in our fingerprint. So currently we have a radius of 2 in our Morgan fingerprint. So we have all these nice circular environments in there. Now imagine I put the radius to 0. And in that case, actually, we will only have atomic information. We will not have any kind of connectivity information. So we can have a look how much our performance is going to deteriorate when we do this. And in case the models are still too good, it's another sign that the task is really on the easy side. Yeah, so here we can see actually the MCC, it very slightly deteriorated, but it's still like working very well. So like most likely what this means is that there are some underlying things about our active data that's making it too easy for the model to find these compounds. Actually, if you think about it, it makes sense because you could say if you build a mental model of what's a D3 binder, you could say basic amine, some aromatic rings, and all those things you can actually express as strictly atomic features. So this is in part why this task is so easy. Okay, so let's return to normal size fingerprints so that we can keep on going through this notebook. Yeah, it's gonna take a second. Yeah, and so here again, we do the same thing. We load up those zinc smiles. Here in this case, I'm adding the name of the molecules as a property, just so that I can display them in a little bit cleaner way afterwards. And then again, I'll put them here in the already trained classifier model, predict their probabilities, rank them from most probable to least probable, and display the best 10 or 20 or something like this. Yeah, in this case, actually, I have the best 20 displayed there. So let's have a look here. Yeah, and here also now I'm rendering them as a grid. So it's a little bit nicer way to see them all at the same time. And actually, you can recognize in here basically the same molecules as we had before. So we had different random seeds and so on, but it's robust enough that it's still like ranking everything in this zinc dataset the same because it's just like finding and recognizing those piperazines in there. Cool. So for this notebook, for the first out of 2 notebooks, conclusion is clear. The virtual screen gives some nice molecules. The classic motif is in there, but well, the task is a little bit too easy because even a KNN works there. So now let's switch to something a little bit more tricky, and that's AutoMap properties. And for this, I have a set with about 1,000 molecules in there, and they have a label. Do they penetrate the blood-brain barrier or not? Which, of course, is a very important property of molecules because in some cases, it's extremely important that it does. For example, if you're making antidepressant or something like this, you don't want it to be strictly peripheral. In some cases, it's absolutely necessary that it doesn't cross the blood-brain barrier. For example, when you are making next-gen antihistamines and you don't want people to get drowsy because of actions at CNS, various CNS receptors. Very useful ADMET property. Yeah, we can even have a look inside here, how that file looks. Yeah, so they're even in there with their names. So most of these are uh, marketed drugs, and yeah, and the smiles is provided here in a column called smiles. So um, let's go through this notebook line by line. So a lot of this is the same as what we did before, but we have some additional things in there. For example, you can see here we are importing the descriptors module of RDKit. And these calculate all these like continuous descriptors, crafty radical descriptors, a few fragment-based descriptors, and so on. In total, it's a list of 200 or so. And in practice, some of them tend to correlate quite well with ADMET properties. For example, calculated log P tends to quite cleanly correlate with that, but even things like molecular weight tend to be affected there. Then to have even a few more descriptors, I'm importing this package called Mordred. And Mordred is conceptually quite similar to the way descriptors are calculated in RDKit. They just have a bit more of them and slightly different ones. So sometimes Mordred is better, sometimes descriptors, RDKit descriptors are better. Yeah, what else is there? Okay, so because I didn't want to manage with any annoying CUDA or NVIDIA stuff, I force the CPU on here just to make sure we don't have to troubleshoot that. And then after that, I import ChemProp. So this morning I was talking about GNNs and their great performance in some open benchmarks. So for this reason, we want to have a look. Will GNNs also work well for this task? Of course, the GNNs will not be so hyper optimized as they were in the case of the Open ADMET challenge. Yeah, and then here, basically, again, we open the data frame and we get the property of interest and we get the molecules. So let's run that and let's see if everything cleanly imports and if it was all installed properly. Uh, hopefully, hopefully it was. Yeah, usually the first time importing ChemProp can take some time. Sometimes even it has to download some pre-trained weights. Okay, that's done. All our stuff is imported. And now, again, we load up our data and we split it up. Again, I'm picking here a random split, which sometimes makes the task a little bit too easy, but I think for illustrative reasons, it's fine enough to do it this way. Another thing is that something like a scaffold split in ADMET properties, this is a little bit less relevant than in predicting bioactivity. So what's happening here? We are splitting X and Y. Here in this case, I'm actually using initials for that so that I can share the same splits across different feature types. And we calculate 3 different feature types. The first type is RDKit descriptors, the second type is Mordred descriptors, and the third type is Morgan fingerprints, the same ones as we were using for our LGBM virtual screen. So let's run this and let's see how long that takes. Um, yeah, so RDKit descriptors are quite fast. Mordred should be a little bit slower. Yeah, that's gonna take a few minutes. So let's wait for that. Yeah, and then once these are built, what we will do is we will try a few classic approaches and classic models and actually see how they compare with each other. For example, often it's said that which exact tree-based model you use, whether it's XGBoost or LGBM or CutBoost or AdaBoost or Random Forest or whatever else you can think of, it's often on par with each other, but still in practice, sometimes one tends to be better than the other. Also, it depends on which hyperparameters you pick. Yeah, so you can see it's completed. It's completed here. So actually, maybe before we build those models, maybe let's have a look what's inside of these arrays, um, just to make this a little bit more concrete. For example, on here, I think this dictionary should be containing all the names of the descriptors that are in there. Yeah, okay, yeah. So you can see here, actually, that's the list of all the Ardiki descriptors. So uh, you have quite a diversity of things in there. Some of them, like let's say, uh, rather easy to interpret, like the molecular weight or the amount of heavy atoms or the number of electrons or something like this. Some of them a little bit more difficult to imagine. Like, for example, there are some descriptors based on the burden matrix, and yeah, and a bunch of descriptors here that are based on partial charges and van der Waals radius, and some based on some cutoffs, making some kind of sum of those. So often the interpretation of these is kind of fuzzy. In case of the fingerprints, it's simple. So if we have a look at the first fingerprint, yeah, you'll just see it's a big list of zeros and ones. And it's actually mostly sparse. So if you'll have a look, the length is 1024, but the amount of ones is 99. So it's 90% unoccupied, which is information theoretically not perfectly efficient, but well, it does the job. Yeah, now in case of the moderate descriptors, um, here I just store the numbers, and you'll just see that there is some huge array here with a bunch of values in there. I think moderate should be something like 1600, yeah, 1610 values. Okay, so these are our features that we have. Now let's see what's the best model, what are the best features. Um, yeah, and so what's happening here is we try out three model types: an ordinary random forest, a light gradient boosting regressor, as opposed to the classifier we used before, and then as something like a baseline model, we use a linear model, we use ridge regression. So how can we use ridge regression and not some other linear model? It's because ridge regression is a little bit more tolerant of correlated descriptors. So the often where some other linear methods fail, this one can somehow deal with it. Okay, so let's run it and let's see. Because our data set is quite small, it's training pretty fast, and yeah, so you can see that it's already halfway. And what you also can see is that the metrics of these models, they are actually not so good. So R squared is around a half. Um, MAE is not all that good. And you can see that actually the very best model we have is like still kind of on the weaker side. Now, the this actually this makes sense because actually measuring blood-brain barrier penetration is tricky. It's known to have a lot of experimental noise. It's known that different laboratories don't agree with each other. So even if you would have perfect predictor, maybe your R squared at best, it can be something like 0.75 or something like this. Another thing is that the underlying factors that determine blood-brain barrier penetrations are a multitude of things. For example, some things cross the blood-brain barrier through active transport. Some of them do it through passive diffusion, and the things that determine whether that's going to be possible or not, they're completely unrelated to each other. Okay, so these finished training. So these classical models, they are very fast, and what turned out to be the best one apparently is an LGBM model with moderate descriptors. Actually, if we compare it with Morgan fingerprints, I would say it's quite a bit better. And that's something which is rather well known. When QSAR modeling admit properties, those descriptors, they somehow tend to perform a little bit better than fingerprints. In part because in fingerprints, for example, the size of your molecule, lipophilicity of your molecule, it's something that you cannot directly extract. For example, the Morgan fingerprint of um, octane and decane, it's the same thing because those bits, they will just overlap with each other, which means that if you have a property that depends on molecular weight or lipophilicity or something like this, you kind of like lose this information. And this is why the performance a little bit deteriorates there. Okay, so now let's move into the future, and let's see if we can do better with ChemProp models. Now, before I explain what's happening here, I'm already gonna run this cell because it tends to take some time to train. In part also because I'm running this here on CPU. Also, I should specify beforehand that just to save training time, the amount of epochs in here is like a little bit on the lower side. I think that's here. So just 20 of them. In practice, if you would be running this in production, maybe you'll run a dozen more, or you'll do early stopping, and only when the performance degrades or doesn't increase for some time, you just stop the model where it is. Oh, actually,
There was that a huge number of epochs will actually produce an overfitted result.
yes. Actually, in practice, anytime I've played around with ChemProp, surprisingly, after a few dozen epochs, you usually already get most of your performance. And after that, if you want to prevent overfitting already, you need to take some care. So very often what may happen is that you do 200 epochs and then you look at the best checkpoint, and the best checkpoint was checkpoint 15 or something like this. Yeah, okay, so actually I have two ChemProp cells here. So what I just ran here, that's basically the vanilla ChemProp. So this is a ChemProp without any pre-initialization. It just for the atoms taking Morgan-like invariants, so atomic number, amount of neighbors, and so on, and it's doing message passing to get embeddings, and then it's using those embeddings in a FFN to predict the properties. Here, actually, I explicitly define quite a few things because ChemProp is quite sensitive for it. So here you can see I'm using the standard featureizer. So that's with this, I actually choose that as my atomic properties. I use these ECFP-like properties. Also, what I do is I scale my targets because, again, ChemProp is a little bit sensitive to that. So often you need to transform your data so that, for example, you transform it into Z values or something like this, because if they are too large, or if they are too broad, somehow it can lead to performance deterioration. You can see here the FFN, the feed-forward neural network. It's pretty shallow. It has 2 layers, 300 hidden dimensions. So this is a rather simple setup. Then all these things I define, like how the MPNN works, what FFN I use. I put that into the trainer here. I get my data loaders because let's say ChemProp is modern, so it takes its data through these more flexible data loaders. So you kind of have to reconstruct this data so that it can read that in the way that it likes, and this actually also makes it possible, for example, to use these APIs to get data from directly from a source like Polaris, for example. Here another parameter that's very important in ChemProp is the learning rate, and one of the reasons why often the performance deteriorates really rapidly is because the learning rate is set a little bit too high. Okay, but let's have a look. Let's have a look at the numbers. So this non-pre-trained model, what kind of numbers do we get? Yeah, so we can see here the R squared actually it's quite bad. It's not even better than our rich models. So and this is probably because our data set is a little bit on the small side. So what we can do in ChemProp is like leverage the pre-trained models or foundation-like models that already were trained on millions of molecules. And the one that we would like to use here is Chameleon. So how does Chameleon work? They train gigantic ChemProp model to predict 1,600 Mordred descriptors. And actually, these happen to be extremely informative, and the MPNN that results from this and the embeddings that result from this, somehow they capture some kind of chemical relations between molecules. And the idea is if we pre-initialize our MPNN with those weights, maybe we will get a little bit better. We will get a little bit better performance. So let's run this cell here, and yeah, this one is definitely gonna take a while. And the one of the reasons for that is that just the amount of parameters is uh, kind of gigantic. So this one here, yeah, certainly I'll have to wait for a minute or five. Actually, while this is running, let me show you some other thing, and we can return to it. We can return to it when it's finished. And that other thing is the probing the models for explainability. So I'm just gonna take the same notebook and I'm gonna duplicate it so that I can run two instances of it. So let me import the same molecules, calculate the same descriptors, and build the same models, and then we can probe them. Yeah. So let's do that here. Yeah, and then that one there. Yeah, and how long did that take? Let's have a look here. Yeah, that took something like a minute, so that's not so bad. Okay, so and let me explain to you what I'm about to show to you. So basically, we are going to use the SHEP package to try to explain individual predictions. So what we want to do is within the molecule visualize where are the predictions coming from? Which atomic and molecular determinants are making the model say this is going to be blood-brain barrier penetrant or not? And the way we will do that is we will take a model that's trained on Morgan fingerprints, and then we will probe the predictions to see which of the bits in the fingerprint are relevant for the prediction. And when we know which of those bits are relevant and how they contribute, we can visualize on a molecule using these colored maps to see where this performance is coming from. So let's see how these, yeah, they are just starting to train. So let's wait for another minute. Yeah, most likely this is a little bit slow because there is competition between all the CPU cores that are doing the ChemProbe here in the one notebook and ChemProbe in the other notebook. Yeah, also here you can see that the original non-pre-trained ChemProbe, it has 400,000 trainable parameters. If you go down here to Chameleon, you have 20 times more. You have 9.4 million tunable parameters. So, and actually that corresponds to more than 20 times slower training times. Cool. So, yeah, and I have to warn a little bit beforehand that this block where I'm doing the shape visualization, it's kind of messy code. For example, I'm calculating the fingerprints using the old API. And the reason why is that it's a little bit easier to get the bit information for it. So that's the reason why, yeah, you can see here I'm calculating them using Alchem method because to get this bit info is the most straightforward in this way. So it's like a little bit stupid to do it this way, or it looks a little bit improper, but yeah, it's easier to write it that way.
Are you getting the majority that?
Uh, oh, I I am not sure I'm not sure if I wrote it as majority bit or if it just takes the first one.
Yeah.
Yeah, I like because the thing is they are for individual predictions. So it means that when you have a majority bit within a molecule, it's like a very pure bit collision. And the typical context in which you would do majority voting is when you do, let's say you train a random forest and you get your feature importances, and it says, okay, bit number 100 is the most important one, and then you can look in all your molecules. What does bit number 100 tend to correspond for, and then you can do majority voting. But that's only like usually on the whole set level. This is like meaningful thing to do. In case this is on the single molecule level that this happens, actually what you can just do is make your fingerprint longer, and you will not have the collision. And you will have a more straightforward explanation. Okay, so in the meantime, these models finish training, so we can run this code book and we can have a look what the output looks like. So, yep.
For these models, we don't need to check if there is any outliers.
Well,
Cleaning.
in principle, one should check it. Or like, let's say if, for example, you build a regression model and the metrics look really bad, of course, then you'll visualize it and have a look and see if there are any particularly bad predictions that are making your metrics so bad. Then after that, you can do some more, let's say, systematic or statistically sound outlier detection. But in practice, if you are happy with your regression metrics, then the outliers, it's like that's an analysis you don't necessarily have to do. And the reason why is that when building QSAR models, it's really about this kind of like hands-off, data-driven correlation type of approach. Whereas usually when you want to remove outliers, it's more, you usually have some kind of like mechanistic reason for it, which here is something like we kind of assume the numbers kind of cancel each other out. And the fact that you may have a few outliers in your training set, or you may have a few like particularly bad predictions or something like this, that just like, well, every model has its limitation and you can just take that as it is. But it may be that if you remove the outliers, if you clean up your data properly, you will get better regression metrics. Okay, so in the meantime, let's have a look at what Shep says here. And you can see here, basically, I picked two molecules, one very greasy one that can enter the brain quite efficiently, and then here one ultra polar one that well, actually, because it's a sugar, you can kind of discuss how well that will get into the brain. But here, actually, it's not about how accurate our prediction is. Here it's about, according to Shep, what is the explanation that our model gives for why it made a prediction of this type. Yeah, the color coding here is red means increased blood barrier penetration. Green means decreased blood barrier penetration. So what's happening here on this map, it's kind of, yeah, this is kind of logical. Even if it's not true for the sugar, the more aliphatic alcohols that you will have in your molecule, the less likely, of course, it is that it will cross the blood-brain barrier. Likewise here, on this molecule, it's recognizing this kind of, again, this piperazine ring and these sort of like lipophilic elements that often are associated with this CNS penetrant lipophilic molecules. So all in all, you could say that the Shep analysis here is rather following intuition and rather in line with what we would think. And yeah.
Does this also convey like the size of the molecules? Does that also involve it influence the permeability, especially?
Yeah. So here in this specific case, no, because we are probing it using Morgan bits. And actually, as we were trying to explain why our Morgan-based models don't work too well, actually the reason why is exactly this factor that you mentioned. But on the other hand, if you want to, like, visualize the dependency on, for example, molecular size, anyway, with a color map, it would be like not so straightforward to do that. But it's true that actually if you would try to interpret the models based on descriptors, you will see that actually these size correlated, lipophilicity correlated descriptors, they are really like carrying most of the performance. Yep.
I'll ask, when you look at the glucose or whatever sugar it is, like why did the primary alcohol group actually, why is it like not very penetrating?
No, actually, green here means, yeah, sorry, the color coding is non-intuitive. Green here means the opposite. So green means less BBB penetrant.
Yeah, the primary one is red.
Oh yeah, sorry. Yeah, okay, yeah, like this one. It may be that because it's using Morgan fingerprints that it's taking into account fragments that are centered on this alcohol, but that incorporate this sugar-like substructure. So it could be that it somehow figured out like, wait, actually, if it's a sugar, it needs to be adjusted. But of course, these are explanations of why the model chose to make its prediction. And actually, when you have a kind of like weak model with R squared of 0.5 like we have here, it may well be that first of all, the predictions are completely wrong, or second of all, the reasoning that leads towards correct predictions is also completely wrong. And basically, what we see here is just the reasoning that our fit had. Okay, let's have a look and let's see. Yeah, I think that ChemProp it's still training, so it's taking a super long time. But I would say with running the SHEP, we are basically finished here. So let's finish the session with any kind of like open questions you have or any troubles you ran into running parts of this notebook or any other follow-ups that you'd like to hear about or see. Yeah, and if there are no such questions in that case, I thank you. I thank you for your attention.
Those ones are running specific on CPU, or is the GPU available as false?
Yeah, it's like often ChemProp it can run almost as fast on CPU as GPU, but here somehow it tends to be really slow. But I deactivated GPU actually mainly so that it doesn't mess up with various different NVIDIA drivers, CUDA versions, and so on all these devices here.
But if the developer uses that like predictions and then it does
Yeah.
well really nice.
But I guess it's when it's
Yeah.
very big library.
Yeah. Okay. Actually, one more thing to say. The model just finished, and we can actually see the pre-trained ChemProp compared. So this is the non-trained. It had R squared of 0.3. The pre-trained one has R squared of 0.532. So actually, the pre-training it does contribute something. It's still not such a good value, but it's much better. Yeah. Okay, cool. So thank you to the online people as well. I'm gonna mute myself now and enjoy the rest of the conference.
On, and we are online. So this one. Before we will start, I would like to ask you to run Ubuntu on those computers, or if you previously installed the environment for EasyDoc tutorial, it will work for this tutorial as well. So on your laptop, you can also start the environment for EasyDoc. All instructions were provided on the Discord channel. And when you will start your, it's pretty nice. When you will start your okay. When we will start Ubuntu, you will see the command line shell And then I would like to ask you to execute these two commands. You can find these commands in the Discord channel as well. So I provided here, you can find them. These ones, these two commands, just copy paste. First one, enter, it will be executed in seconds, then the second one, and it will be executed for several minutes. So the first one, it will create the necessary folders, download data files with a notebook, Python notebook, some other stuff, and the second one will download the fragment database. It's relatively large, but no, it's small because we have much larger database. This database should be something like in zipped format less than 300 megabytes, in unzipped something like 1 gigabyte. So it should be enough place on your computers, I hope, for that. And yeah, I hope that almost all of these computers which you occupy should work. If you will not find somewhere this CReM-add environment, then probably it's better to switch to another one to check whether you have an environment on your computers. I mean those ones which are in the classroom. You can just type conda env list, and you will see the list of environments, and there should be CReM-add9. So this is just the check that your computer is set up for this story. So return back to those comments maybe in the Discord. Oh, it's not Discord. This one, yeah. So please execute them, and when you will start the execution, we can continue with explanation of some theory between. So is it okay? Yeah. Yeah, the first one, then the second one. So the full lines and copy paste to the console.
I'm sorry, I need obligatory to access to Discord or
How else we can distribute?
okay, no worry.
I'm just trying to remember where I also put this. Yeah, you can try to type in, but it's too complex.
The rapid access.
Which, yeah, we have to think about some faster. So someone else also have problems to access to Discord to copy paste these links, because I can just create some short link. Okay, so I will make a small document maybe, and you will be able to download it. Oops. Ah. Oh. Hmm. So here is a USB stick with materials. So if someone needs, so you, you already. So here you can download. There will be two PDF files. One is a presentation. The second one is instruction. Just copy paste both. Let me maybe. It didn't work. Go to downloads. Go to downloads and copy paste here. You don't need to do that. Just copy paste here. Yeah, it works. So you just need to open here, and here you can find these two commands. Just copy paste. Here they will be with a line break, so you should create a single line from this and execute it. So someone else, yeah, here. So there will be two PDFs. One is slides, which will go through, and the second one is a tutorial. And in this tutorial, you will find the links as well. So just open the tutorial PDF, and there will be two commands. Yeah, one and the second. Copy the whole line, but it will be a break line at the end. So you need to create a single line without line breaks. So copy paste to some text editor. This should be executed in the Ubuntu. So start Ubuntu, like preview here, Ubuntu, just type, it's here already. And insert here, and it will create all necessary files. But you should, if you will insert, it will right mouse button. But check whether it is, yeah, by pieces, by pieces. And paste. No, it is good. Yes, it should work. Enter, yeah. So yeah, this is a single command, yeah, but by pieces. By pieces, copy paste. Right mouse, paste, and then second line. No, not enter. You have to combine all, yeah, space, and then you have to combine all these lines in one long line. Yeah, this is okay. Yeah, you can open and text editor and then create this long line and then execute. So there are two lines of commands, just two. Yeah, in PDF it's not so convenient. So did you succeed? Yeah, it's okay. Yeah, you will wait. There are some couple of minutes, but it doesn't matter because we will start from some theory. I just want to be sure that this fragment database was transferred properly. I do not see well.
Yeah.
It doesn't matter where you are, because commands are written in such a way so you can run them from any directory. I just want to check whether it's completely correct.
That means it wasn't, that was.
You already executed this line successfully? I don't see this because it should create you more dash somewhere missed. Yeah, this one.
But why it was missed? Ah, okay.
Because you didn't copy it, that's okay. Yes. Now it creates the directory structure and then you execute the previous command because they should be executed sequentially. That's important. That's important. So it will download, unpack it, and it will be ready. So everything is ready, yeah? Excellent. So let's start some theoretical part. Yeah, it will take 3-5 minutes, these downloads and unpacking, so don't worry. And we go here. Okay. So, the time, okay, 15 minutes passed. CReM is a fragment-based approach, which we developed something like more than 5 years ago. And it became quite popular. So currently there are something roughly 4,000-5,000 downloads per month. And it is also a highly cited approach. It is used in academia, but since the number of citations is much less than number of downloads, I expect that it is widely used in industry as well. Again, we also have some contacts with industry who use this approach internally. There are a lot of advantages. We will point of them later. So synthetic accessibility of generated molecules, flexibility of how you want to transform your molecules. But I would like to start from the point of comparison, because currently maybe the mainstream approaches in de novo design are reaction-based one. Because everybody wants not to just design, generate structure. It's quite easy. It's quite easy to generate structure, but it's very hard to generate synthesizable structure. It's still very hard problem. And even those modern neural network cannot solve it completely on 100%. So, and despite these reaction-based approaches are mainstream, fragment-based approaches, they may propose you some other advantages. And with some tweaks, like in CReM, they can also control synthetic accessibility of generated molecules. So here is a just prerequisite for both class of approaches. So reaction-based approaches, they need just the set of reaction rules and the library of building blocks. And the diversity of output molecules purely depend on these two positions. So how many rules you have, how good these rules, how they well describe the transformation, and how diverse and large libraries of building blocks you submitted. And this give you the greatest advantage that the designed molecule should be possible to synthesize, because in addition to this, you also design the reaction pathway, how you construct these molecules from building blocks. So that's really a great advantage, especially for industry. However, in the terms of the exploration of a chemical space, reaction-based approaches have some limitations. Yeah, diversity, as I told you, limited by the number of building blocks, reaction rules, that's okay. But when you think about the chemical space, like multiple molecules, with the reaction-based approaches, you cannot jump from one molecule to some arbitrary another molecule. It's impossible. You can only follow the reaction rules, and that's why those orange arrows, they demonstrate that, okay, this transformation is possible, but those transformations are not possible. So even compounds which are quite similar, for example, like this acetophenone, or toluene, they're quite similar, quite close, and in the fragment-based approach, they can be quite easily transformed to each other. But in the reaction-based approaches, this path of exploration is completely forbidden. So that's why you are limited in moves in chemical space. This also additionally complicated that what I know, and I didn't see any other examples, only coupling reactions is used. So you explore your chemical space only in forward manner. You cannot make backward step. For example, if you get stuck in your search algorithm somewhere here, you will not be able to return back and switch to another branch in this search tree. So yeah, it is possible with Monte Carlo tree search to some extent to make backward steps, but that is really complex, and this also complicates this stuff. So what can be done with fragment base in one step here will require a lot of additional steps to make. Some molecules due to this could be unreachable because you don't have specific rule or specific building block to reach them. So these regions, for example, like here, some molecules may be unreachable. So in fragment-based approaches, when you just try to combine fragments in different ways, you can move in almost any direction. So you can replace whatever fragment you want with another one and make some huge leaps, like on many hundred, very distant. So you can change a lot. You can keep only one atom and replace everything else, for example. So you have a lot of freedom in the exploration. It gives you a lot of flexibility. And in this case, it covers much larger chemical space as well. Of course, it also depends on your fragment library. But the fragments usually are small molecules, something like up to 12 heavy atoms, and the number of such fragments are relatively limited rather than the number of building blocks. Building blocks can be quite large also. So here you can try to create something large, complex from very basic building blocks, like fragments. However, the main challenge here is how to link these fragments, because, okay, you can draw the bond between any kind of atoms, and you can even don't break the valency rules, but it doesn't guarantee that this molecule will be synthetically accessible. So it's really challenging, really challenging. And actually, CReM is answered and addressed this particular question regarding synthetic accessibility. So this is a paper which was published in Journal Cheminformatics 5 years ago. So CReM is the chemically reasonable mutations, and the idea behind is extremely simple, and maybe you're already aware about matching molecular pairs approach. This is pretty much the same with some additions, some very small additions. So here we have already existing molecules, so which were previously synthesized. So we know that, okay, these molecules are synthesizable, at least by some chemist. This could be Campbell, PubChem, your proprietary library, or library from some vendors of compounds. Then you exhaustively fragment those previously existing structures. So you cut single bonds in different combinations. Here I just demonstrate one example. So we cut 2 single bonds at a time. And in this case, we create fragment and these remaining parts. And we create a database of fragments from this information. So we took the fragment, and additionally to fragment, we annotate its attachment point with the context of a given radius. So in this case, we took radius 3. It means that we take up to 3 bonds away from the attachment point, this part and this part. And we store this like an additional information for each fragment. So each fragment are annotated, but its chemical context. And we do this for each fragment we create in this fragmentation way. And then we store this, and the idea that if we have fragments occurring in the same chemical context, it means that they are mutually interchangeable. So we can replace this fragment with this one in this chemical context, and with a high probability we can obtain synthetically accessible compound. I will explain you how to tweak synthetic accessibility, but generally this may work. It will depend on the radius of this context, how large context we consider. And to perform quick replacements, quick search, we store all these fragments with annotated contexts in a single database table. So keys are our context, and there are some associated fragments with this context. And when we have a new molecule, for example, this one, and we want to replace some fragment, for example, this one highlighted in red, again, we cut it, and then we define a context of a given radius, again, 3, like in the previous example. So here we get the context of radius 3, and then we search this context in the database. And if we find that this context exists and there are some molecules associated with this context, we can perform this replacement. So we replace this fragment with those fragments from the database to create the new list of compounds. So very simple, extremely. Not a rocket science. But it is very efficient. So in this case, you generate always chemically valid structures, and you can tweak the synthetic accessibility of them. This was for a long time a major problem of the fragment-based approaches. So because previously fragment-based approaches, they ignore the context and they try to link based on some probabilistic statistics or something else, but they didn't explicitly encode this information. Here are just summary of features which we implemented. So we have 3 modes. So you can expand your fragment, add new fragments to existing. You can mutate them also. So you replace some heavy atoms with another group of heavy atoms. Actually, growing is just a particular case of mutation. In growing, you mutate a hydrogen. In mutation, you mutate some heavy atom group with another one, or you can even link 2 molecules together with a linker. This can be also address some cases when you have, from fragment-based screening, fragments occupying different sub-pockets in a binding site, and you want to find the linker which can connect them. So it can be quite useful. There are some other additional features which may be not so relevant for academics, but for industry. So you can use your own in-house database of structures previously synthesized to create your particular fragment database. And in this case, this developed fragment database may be more relevant to chemical space accessible to your chemists. So this could be also a way how to tweak synthetic accessibility. As I mentioned previously, the size of a radius will control synthetic accessibility of the designed compounds. We will discuss this a little bit later. Then you can specify the size of the replacing and replaced fragment. In this case, you can control the granularity of your search. So because for example, in the very beginning, you may want to make huge or large steps, jumps in the chemical space, but when you will find a good favorable space of compounds with a good properties, then you would like to make small steps, small changes in structures to finally explore this local chemical space. So this is also possible. You may also protect some atoms. So for example, you have molecule and you want to avoid the changes of a scaffold, so you can specify which atom you want to protect, and they will not be replaced during these random mutations. Or you can specifically say that, okay, I want to replace exactly this atom or this group of atoms, and then replacement will occur on this selection, for example. For a linking algorithm, we have also a distance between attachment point, and this also may be useful. You can specify how long this linker should be. So this additional way how to tweak the generation. And all these features, they help us to address different practical tasks like scaffold hopping, enumeration of analog series, expansion of hit molecules, fragments, or lead optimization, and of course de novo design, where we generate structures completely from scratch. So yeah, here is examples how radius of chemical context may work. So we have this molecule, benzene ring with 2 amino groups, and we ask to grow this structure using up to 2 heavy atoms. So we want to add very small fragment to this molecule with different radiuses. And these are example what we can get from Campbell database if we will ask for this action. So it generates, I don't remember, something like more than 50 compounds. And as you can see, it put these additional substituents in different positions to benzene ring, to nitrogen, so quite a lot of them. If there are some chemists in the audience, you can try to evaluate, are these all molecules feasible, or some molecules are completely forbidden or hardy or extremely hard to synthesize. If we increase the size of a radius, the number of generated compounds will decrease, and it will generate only this number of compounds. So these compounds will not be generated. It means that with radius context 2, these fragments cannot be attached. So it means that this fragment or this fragment exists in some existing molecules where it attached to aromatic carbon. So it's okay, but it does not exist in the case where this fragment is attached to one aromatic, which are attached to another 2 aromatics and branched here. If we increase further the radius, you can get even smaller number of compounds. So this means that these fragments, which were added in this green spot, in this green area, are not occur in the environment of 3 atoms away. So 1, 2, 3, 1, 2, 3. So almost the whole ring system was already considered with this substituent, and there are no examples in Campbell where this substituent were attached to this pattern. So in this way, increasing the radius, you decrease the number of compounds, and you increase the probability that, okay, this replacement may be really synthetically feasible. And what will be, if you switch to radius 4, we will have just 2 examples. So methylated and ethylated derivatives, nothing else. With radius 5, probably we have nothing. Yeah, with radius 5, we have nothing. So just an example, how it works. Another feature, I will not stop on it in too much details. Yeah, I will try to speed up a little bit. Another feature is that you can create chemical motifs, new chemical motifs, which are larger than your radius. So if you, for example, remove compounds with amide group from your initial set of compounds before fragmentation, and then you will try to generate new structures and you will choose the radius 2 or more, you will never generate amide derivatives. Because with this radius, they not exist in the database. So if your radius capture particular motif, this can be recreated, yeah. Okay, so these are example how we estimate synthetic accessibility. Because many times during this workshop it was mentioned, and actually these are citation of the work of Peter Ertel. It's quite famous work where he suggested quite simple algorithm to estimate the synthetic accessibility of compounds. So there is a simple linear equation where molecules can be assigned score from 1 to 10, where 1 means synthetically accessible, almost available, and 10 means something extremely complex. Here you can see the distribution of values in Campbell of SA score, synthetic accessibility score, and you can see that the median value around 2.7, the average mean value is around 3, and here is just examples how this score correlate with the structure complexity, just to get the perception how it looks like and what is score good, what is score bad. In our work, we mainly consider that scores below 3 is good and acceptable. You may find in literature different opinions. Some decide something scores like 4 or more. I don't think that it is relevant. Another way how you can tweak the synthetic accessibility, okay, radius. Radius, this is one thing. Another thing that you can pre-filter your initial compound, your initial structures before fragmentation. And for this, you can use, again, synthetic accessibility score. So here we started from Campbell 22 with 1.5 million compounds, and we removed all potential structural alerts just to avoid to the recreation later. And then, so we got something like 800,000 structures, which were fragmented on up to 1 million fragments. And this is like a whole Campbell. But then we can filter those structures by synthetic accessibility. And in this case, we select only compounds having synthetic accessibility score below 2.5 or even below 2. And these are quite small number of structures in Campbell, and they can be also fragmented. And we have, in this way, different fragments. So these fragments are from mostly accessible compounds. These are from also moderately accessible, and these are from whole Campbell. So we don't know how easy to synthesize them, because yeah, they were synthesized previously, but it doesn't mean that it will be easy to repeat the synthesis. And yeah, in this case, we get much less number of compounds, fragments. And here we just compute the estimate. So this is a theoretical estimate how many compounds can be generated in the growing mode using these fragments. And here you can see that if we use the full fragment database and radius 3, we can synthesize 10 power 17. If we go to more restricted fragment database with the same radius, the decrease is less than 1 order of magnitude. If we go to another even more restricted fragment database using the same radius, we can again decrease just 1 order of magnitude output. So even from such a small number of fragments, just 55,000, we can recreate and cover quite large space. quite large chemical space. So this is something interesting. So even increasing the number of starting fragments will not increase somehow exponentially. Yeah, it increased somehow, but it will not be like an explosion. Okay, so here is a link on CReM databases precompiled. This link is also available in the PDF file which I sent to the channel. And here is example how many compounds can be generated using different radius and different fragment databases, just to compare. So again, we ask to mutate, in this case, not grow, but mutate this structure. So replace something. In some cases, the replacement is quite huge. So it replaces completely the benzene ring with something. And here you can see that we increase the radius, the number of compounds is also decreased. We took more restricted fragment database, number of compounds proportionally decrease and decrease with the radius. So these are just demonstration how predictably changed the number of generated structures. Okay, so let's now start some hands-on experience, and you can run the website. Here you can find the link, CReM.imtm.cz. Yeah, it works. Perfect. Let's try to make it maybe larger a little bit. Okay. So this is a very simple web application. It doesn't provide you a lot of flexibility and a lot of options, but it provides you some basic stuff to be familiar with this approach. Some researchers use this website to really generate some structures which were they then explored, evaluated with QSAR model or MD simulations, whatever, publish their papers. So here you can draw some structure. For example, this one. I don't know. Maybe here some methyl. It's not that. Maybe, okay, this is acceptable. Okay. And then you have two modes, scaffold mode and analog mode. Scaffold mode means that it will make replacement of selected atoms. And analog modes, it will replace all or sorry. So scaffold modes, it means it's a decoration. So it will decorate your structure. And analog mode, it means that it will replace some fragments. So scaffold, it's a growing approach. Analog mode, it's a mutation approach. And when we will use this web application, the replacements can be done in a random position, or if you will select particular atoms, it will be done on selected positions. Here you can also specify which database you want to use. So these are Campbell, synthetic accessibility is filtered by synthetic accessibility score and additionally by alerts. For example, we choose this one, so somewhere larger without alerts. Here you can specify the context radius, number of replacements, so you can control how many compounds you want to retrieve back. You can specify up to 10,000. It's absolutely possible. It's very fast, but just to be easier, we can just keep 5. And the maximum size of a fragment, you can also adjust if you want. And in this case, okay, we can select these two atoms. We can select scaffold mode and click generate, and it should create structures which are have substituents at these positions. So here is a list of smiles which were generated. We can store it somewhere in a list of molecules. Okay, let's do this here. TSV. Okay, replace. And then we can open Data Warrior to look on these structures. You also have on these computers installed Data Warrior. Actually, it was recommended to install it during the installation and setup of your environment. And then we can open this file. TSV. The first line was recognized as a header, and here you can we can change here. So horizontal, yeah, something like this. So here you can see these structures. So we asked to substitute these two positions, and it suggested some replacements with radius 3. So it means that, okay, these fragments were observed in this large chemical context. Yeah? Okay, we can go back. And you can, for example, want to replace some part of a molecule with analog mode. It means the mutation. If you will not specify atoms, it will try to replace all possible fragments, single atoms, ring systems. But for example, we want to replace this phenyl group. So we select phenyl, select analog mode, keep everything else the same, click generate, and in half a second we got the response. So as we asked just 5 structures, we got just, we can add in the beginning some faked title and then open this file again. So open recent, one TSV. So yeah, that's it. So in here you can see the structures which were generated. So it replaced the phenyl group. Phenyl group keeps methyl and piperazine ring. So, and those molecules should be again synthesizable since we used quite large radius. Sometimes it may happen that you specify some large radius and it will return you nothing, 0. It's also possible. So it means that, okay, these environments are not exist. And in this case, it's your choice. If you decrease the radius, yeah, you will get some molecules. But whether they will be accessible or not already will be the question for your chemists. So these are quite simple way how to visually generate structures without even knowledge of Python, whatever. Even medicinal chemists can use this website. Yeah, there is a limitations, but that is possible. Okay, so now we can switch to shell. So you have your Ubuntu shell. So you have to switch to the directory where you extracted those files. This should be CD, ADD, you can, okay, let's try to make it in a more reasonable way that you will see the commands. So I created the same directory structure as you. So CD, ADD 9, then CReM tutorial, and that's it probably. Yeah, that's it. So just go to this directory. And then do not forget to activate your environment, conda, activate CReM ADD9. Yeah? So everybody succeeded with that? Does it work? Yeah. Is it okay? Yeah. So you could reach it. So you activate it. Yeah, yeah. So perfect. So is it okay? Yeah. Is it okay? Yeah.
I think yes.
Yeah. It seems
Okay.
it seems good. Seems good. Everything fine? Perfect. So let's go. Now you just type Jupyter-notebook. So Jupyter-notebook and press enter. In my case, I will see the opened browser. In your case, you will not see this. So you should copy this token, copy the whole link, and insert it into the browser in Windows. So you can just go and insert this link, and it will open the notebook finally. So just look on Jupyter-notebook. It should be installed already with this environment. It may take a little bit time to start, and then you can just copy. Yeah. So just copy the HTTP link and insert into your browser, Edge, Firefox, whatever. It will work in any browser. So some problems?
Jupyter.
Dash, not slash, dash. Yeah?
So it's
Oh.
the same.
No, you have Jupyter, not Jupyterer. You
Copied here, so I don't know.
Oh, it's wrong. There is a mistake. Thank you. Yeah, you find it. So without this R.
Jupyter.
Jupyter. Yeah. So there is a mistake in PDF file. Yeah. We discovered it. Thanks. Yeah, without just Jupyter. There is Jupyterer. It's a wrong spelling. So it works, yeah? No, you could not?
I closed the terminal now.
But you can always open it. It's no problem. Then just go to the directory, go back to the terminal. There is no this command. But you already did this.
What?
You already did this.
Yes, but I closed the.
It doesn't matter. Everything was already installed. You call this command just once and everything's set up. So now you just need to switch to the directory. Go back to the console.
Where? No,
Write the command.
Yeah.
After that,
You should copy the link, this link.
which one?
Any of them.
Okay.
They're both identical. So copy to the browser, to the internet browser.
this code.
Before that, yeah, you need
I mean,
you need to switch to the directory, go back to console, then cd, small one, space add9, dd9 slash
Where is?
slash
Yeah.
here, and then no, again caps lock, no, CReM tutorial, you're inside. LL, you see this command, you see this notebook. Now you type conda, activate, and the name of the environment, CReM-ADD9. Oh, so this computer doesn't have it? Okay. Yeah, and now type Jupyter dash.
Yeah.
Jupyter.
Yeah.
Dash notebook.
Dash.
Short dash and notebook.
Okay.
And we start, it will autocomplete. Jupyter. Here is the Y.
Okay.
And then, yeah, this one.
Folder is a CReM, folder.
Yeah?
This one?
No.
No?
We will run the notebook and this HTTP link, you just copy paste and insert into the browser. Yeah, so you're here. So could you open the, no, there are some problems. You don't need to open this file. I didn't tell about this, so just open the link, not the file. Yes, because first you need to activate the environment. So conda activate CReM-ADD9. Conda activate. No, not this one. Conda activate. Conda. Space activate.
Poi spazio. Activate. Via.
Activate without D. Space and CReM dash.
Dash trattino.
Tino. Trattino.
Aspetta.
It's here, but CReM means without R. So, and then ADD9. Yeah, it's activated. And now you can go this command, but here is a misprint. Yeah, and just remove this one. With R, yeah, and enter. No. No. Look, R should be removed, not P. Yeah. Yeah, and now you can copy this link HTTP to the web browser. So you also have the same issues, yeah? Yeah, maybe. Yeah, you also have to activate. First, conda activate CReM-ADD9. I may help you with that. So conda activate CReM-ADD9. And then so it should work. Yeah, so you can just copy this link to the web browser and it will open the notebook. So everything okay? No? Yeah? Some errors. But, okay, so see you. Thank you.
I don't know how.
Let's you. So you open it.
Yeah.
You don't need to open some files. It's not necessary. I didn't say, so just wait a little bit. I just want to be sure that everybody run it. Okay, I see. Good. It's fine.
Yeah, I just installed the dependencies.
Okay. So Perfect. Now we can go. Some problems? Okay, perfect. Good. So I will enlarge a little bit the interface. And here we can open this CReM file. So here just click and open CReM IPNB. So this is a notebook with commands. It will take some time to load, but everything should work. You can make kernel, restart kernel, and clear output of all cells to be sure that there will not be some interference with the previously executed cells. So choose this option. Yeah? Okay. So click restart. It will restart in just seconds. Okay. And now you execute, and I will explain what happens, how to further tweak, and how to use this tool from Python, because this gives you maximum flexibility, what you can do with these tools. So first cell is just import of different functions from Python, RDKit, CReM, then couple of functions which will visualize our structures. Here we define the database name. So if you execute all previous command as it written in the instructions, you should have a DB file in the directory CReMDB. So this will be the source of fragments later. And then we can take as a starting molecule the ligand from EasyDoc tutorial. This is the ligand from 3-RAL X-ray structure. So here it is on the screen. So I think that until that point, everybody should succeed it. So it's quite easy to reach. And now we just perform manipulations with this structure. So here is a basic generator. So we use grow mol. We specify the mol object, name of the database, and then we specify return mol true to return mol object. By default, it will return just smiles. And we will execute it, and it will return us 63 structures. And we can look inside. Mols would be the list in Python, consisting of lists of 2 elements, smiles and mol objects, and we can remove smiles and keep only the mol object by executing the following command. And then we can visualize those mol objects. So here you can see examples of generated molecules. And with the color, it is highlighting the fragment which was added to the structure. So we can just control that everything works fine, because if something doesn't work, it means that there are some errors in the path or databases or something, what knows. So it works good. Yeah, you have some.
I do have different structures, yeah. So basically, it's like randomly chooses which hydrogen it iterates.
Yes, by default, the tool tries to replace random hydrogens or random fragments, but further you can point it out which you want particularly to replace or grow. So everybody succeeded. It means that everything was set up properly. Is it working? No? In Jupyter.
What? Yeah.
So you should go up to very start. Then you should kernel, restart kernel and clear output. Yeah, agree. Restart, and then execute first, and then you can put it here as a cursor and then Control Enter. for example.
Yeah.
No, it's not necessary to
Okay.
select. Just stay here and Control Enter.
Okay.
Yeah, and then the next one you can use mouse like Control Enter. Is when it is executing, it is the star. When it was finished, there will be the number.
Okay.
So you can go further. So this one, so it's okay. The next one, it's also okay. And then this one.
Everything.
Yeah, here is the error because there is something problem with setup of your environment, and we have to go back to.
Yeah, but
So database does not exist. So we need to switch back to Ubuntu. Open the new window. Right mouse button. Once more Ubuntu. And type. Type. But you have files, but you don't. So you didn't. Maybe you close the window without finishing the command. So you need to execute maybe the. Okay, let's test. Slash CReM. 3 not found even. Okay, then. CReM db, it's empty. So you need to execute the second command. You didn't finish until
okay.
it finished. If you have opened it some way, it's not. So you need to copy all these 3 lines once more to the text file, and then these 3 lines, all 3 lines. And yeah.
And after that, I write.
Once more. So you execute all cells.
Yeah.
It works. It works. No. In text file. In text file, here is open. Yeah. Just and create a single line. So remove. Yeah. And then copy this line and execute it. It should work. But it will take you something like 5 minutes, maybe.
Yeah.
Not here, in another one. Yeah. Right mouse button. Yeah. So it will take, but hopefully not that much time. So that's why I asked to do this in the beginning. And you shouldn't close the console because it interrupts the execution. So here also. Yeah, so is not defined because you didn't execute all cells before. So you have to execute them consequently.
Yeah, I did that.
No.
From there.
No.
Go up. I started.
Yeah, only this one, but not this one. And it is not even here already an error was. So it means that let's check what could be. So you run it from which environment? Many errors. Yeah, you run it from another environment. So yeah, it's necessary to, before that, activate the proper environment. So we can break it. First, we have to activate conda. Activate CReM -add9. Oh, terrible. What is the language? Check language. Okay. And then once more. And it will be much better already. It should be. And then open again. Logic. And then open this. Okay, and now try to execute the first cell again. Yeah, you can remove. Yeah, you can remove all of them, and then execute first one. Okay. So
There isn't a way to do
so
together.
that's enough.
Is there a way to do it together?
Yeah, you can go till the end, but nevertheless, I will explain each step
Okay.
because, yeah, it works. Nice. Here need to install it. Okay. And here is also still downloaded. So we will go a little bit forward since we are short on time. Okay, so we demonstrated just first example how to grow molecules, and they're growing in some random positions. What else you can tweak? For example, in the next cell, you can specify the size of a fragment which will be attached, and you can specify the minimum fragment size and maximum fragment size. This is the arguments of grow mol. In this case, we specified 4 and 6, so this should be some larger fragments added in some random position of your initial structure. So we generated more than 400 compounds, and here is examples of these structures. So yeah, you can see they have from 4 to 6 heavy atoms. And they were attached at this position. Yeah, all of them in the same position, but it is just because we took the top list. Okay, so here we can specify, for example, we can increase radius. With the same settings as previously, we can increase radius from 3, which is a default value, to 5. And we can get already just 79 compounds, 79 structures instead of more than 400. And here is their structures. And they, at least in the beginning, mostly substituted at the nitrogen in sulfonamide group. So these are just show you, okay, structures will be less number as we seen on the in the presentation. And now, if you want to have more control, if you want to specify particular positions to which we want to make to which we want to add substituents, we can draw the structure, draw the ID of atoms, and then, for example, we can want to populate these positions, which are 0, 11, and 13, to attach new fragments, because if you look at 3D structure, we will see that there are some space to occupy by additional substituents. And then we, again, run the same command as previously, minimum size 1, maximum size 2, radius 5, and replace IDs of these atoms in RDKit, which are starting from 0. And we can generate just 7 compounds. So just 7 with these restrictions. So radius 5 and up to 2 heavy atoms. And here is a structure of those molecules. So you can see some of them were attached to this position, some of them another position. They're not so numerous, but with a high probability you can synthesize or purchase the building blocks to synthesize those molecules. Yeah, so some small.
The higher the radius, the higher the chances that the molecule would be synthesized.
Yeah. So that's why we choose large enough, but yeah, if you choose radius 5, you can get just few suggestions. That may be not enough for your study. But up to radius 3, I would say it's more or less okay. With less, I would suggest to use a very restricted fragment library created from very synthetically feasible structures. In this case, this can compensate the decrease of radius. Okay, so we can switch to the mutate stage. Just just to check. Okay. So switch to mutate option, and we also pass the same molecule, database, everything by default. And it will generate, I expect, something like more 2000 structures. Because currently we do not limit the number of generated structures, it generates all possible structures. And for large number, it took some time, few seconds. Yeah. 2194. And here you can see how these structures may look like, so how large replacements could be. Some of them could be small, some of them could be large. So yeah, at different positions. Now, what could be practical use case? You want to replace particular group with another one to generate the analog series, which can be useful, for example, for free energy perturbation studies. Again, we display the IDs, and for example, in this case, we want to replace this methoxyphenyl group with some other suggestions from the database. So we write these IDs of atoms which we want to replace. Here they are, and specify as replace IDs argument in our function, and we got 142 possible replacements. And here we can draw some structures. So in some cases, we see just small replacements. So not a whole fragment was replaced, but only part of this fragment was replaced. So when you specify the IDs which you want to replace, it doesn't mean that all this atom will be replaced at a time, at once. So it means that all or some of these atoms could be replaced. And here you can see, in some cases, the whole fragment was replaced, like in this case, or just substituent, or just one atom, or hydrogen. And if you want to replace a whole fragment, you have to explicitly restrict the generation. So in this case, you specify the minimum and maximum size of the replaced fragment. And if you know that, okay, methoxyphenyl has 8 heavy atoms, you can specify minimum 8, maximum 8. And in this case, all replacements will replace the whole fragment, not just a methyl, methoxy group or something else. So just 68 such replacements. And here you can see the whole fragment was replaced. Yeah, something like methoxyphenyl with phenyl. Yeah, it's also valid. Some other substitute replacements. And here also. So is it clear how we modify? Maybe some questions do you have? How to operate? This is just examples to show you that it may address almost anything that you can imagine. So you want to replace this particular atom or group of atoms simultaneously or just randomly, specific atoms or protect scaffolds. We will show these examples probably later.
I didn't not get mean and max size. So
in the case of mutate mol, it means the size of the replaced fragment. So this means that if we, by default, they are not specified. And it means that we will replace from 1 to maximum heavy atoms. If we specify, for example, from 8 to 8, it means that we replace only fragments of size 8 atoms, 8 heavy atoms. And since we specify that we want to replace only these IDs, only these 8 atoms, these combinations give us that we want to replace the whole this particular fragment. And yeah, you can tweak, you can change these parameters as you want to address again different ideas. And for example, if you want to make reduction of a fragment, because if you randomly choose a fragment from a database, with a much higher probability, it will have more atom than the previous fragment, than which you replace. This is just from purely from statistics, because smaller fragments having two atoms are less number, and large fragments are more diverse and they are more represented. If you want to reduce, specifically reduce the fragment, for example, you want to replace phenoxymethyl with some smaller ring system or small substituent, but you don't want to generate something large, like naphthyl or another phenyl, you can specify this through min inc and max inc arguments. It means that these are increments to the fragment which we replace. So if we replace, in this case, fragment of size 8, and we specify min inc minus 8, it means that the minimum size of a fragment which we took from the database will be 0. So from the size of a fragment we want to replace, we just subtract this number. This is the minimum lower bound, and upper bound will be 8 minus 3, 5 atoms. So we replace the whole fragment of 8 atoms with fragments from a database having from 0 to 5. So it means that it can be hydrogen even, or some fragments up to 5 heavy atoms. So let's execute just 12 examples. And here is the structures. So yeah, some case methyl group, some other small. So here is the 5 atoms in pyrrolidine. Here 4 atoms, 3 atoms, 2 atoms. So this could be the way how, if you want to shrink your molecule, you can exactly, yeah, nevertheless, you can generate all possible structures and then you can post-filter and post-process them. That's also possible. So it's up to you. But if you know about these options, you can really specify from the very beginning and get exactly what you want without necessary to post-process your outputs. Okay, and now we, for example, would like to perform scaffold hopping. So we want to replace some core structure in a molecule with something else. And here in this ligand, as I showed you during the EasyDoc, this fragment is responsible for the interaction with the hinge region of a kinase, so it can be considered like a quite critical scaffold. And we may try to find some analogs of this amino thiazole ring. So we just again write down these IDs of atoms. They're here listed, so 6 atoms, and we try to replace them with something. And again, we will try to replace the whole fragment, so we specify minimum size 6 and maximum size 6. And what we will get, just 36 compounds, and here are their structures. So some phenyls, some benzyls, aminophenyls, some other structures, and those structures, yeah, even some saturated rings can be inserted. So it just make all possible replacements currently from the database. Of course, not all of these replacements will be relevant because, for example, they do not have enough number of hydrogen bond donor and acceptors. But in some cases, you can find some relevant suggestions. Yeah, partially relevant. This could be is here you have hydrogen bond acceptor. There should be some other quite nice structures. This might be, but I don't believe, but it might be to some extent. This replacement, because we have donor acceptor, so it may be will be complementary to the hinge region, because hinge region requires 2 hydrogen bond donor and 1 acceptor, not necessarily all 3, at least 2 may be enough, but yeah, maybe not that many. So this is just an example how we can perform scaffold hopping. The main limitation of CReM, what I forgot to mention in the beginning, is that it cannot create new ring systems at all. So the diversity and representatives of rings in your generated structures will be purely depend on what you have in your fragment database. So this is the only limitation. It's not that much restrictive, but you should be remembered. So it cut only single bonds, acyclic single bonds, so that's why the rings are always replaced as a wall thing. So that's why for scaffold hopping, you will maybe need some diverse fragment library with different ring systems. Okay, so let's... Okay, so link. So now we want to link two molecules which we have. As I explained you, this could be just fragments bound to different pockets in the binding site which you want to connect together. So these are the first one. Okay. So, okay. So we can try to combine this molecule and this molecule. So, sulfonamide and this aldehyde. And we can start, since we already quite advanced, we know these arguments, and arguments are pretty much the same and overlap across different functions. So CReM has 3 main functions: grow mol, mutate mol, and link mol. And those arguments are pretty much the same. There are just in some cases could be slight differences or some additional arguments, but they're quite unified interfaces of those functions. So, okay, we have link mol. We will link these 2 moles using the database, return the molecules, and then in the first mole, we will make connection to the atom number 5, to this one. And in the second mole, we will connection to the atom number 2, so para position to the sulfonamide group. And we want that the distance between these 2 fragments would be exactly 4 bonds. 4 means the number of bonds between 2 fragments. We will show. And here is the number of atoms in this linker. So in this case, we are restricted to the number of from 5 up to 8 atoms, heavy atoms. Yeah, so we executed, we got 46 structures, and here they are. So 1 fragment, the second one, 1 second, 1 second. And if we will count the number of bonds between these 2 fragments, they will be exactly 4. So 1, 2, 3, 4. Again, 1, 2, 3, 4. So in all cases, these are 4 bonds, 1, 2, 3, 4. Or 3 atoms. 4 bonds or 3 atoms. And yeah, since we specify the size, we see just small rings with some substituents or linkers, flexible linkers with aliphatic chains, nothing more. So quite easy. Okay, so now we can switch. So we fill our power and we can switch to even more advanced options. When we develop this tool, so it evolves over the time, so we still develop it, add new functions, and at some point we realize that we need to filter fragments on the fly because we don't want to create some unnecessary structures. We want to avoid their generation at all. So that's why we need to make an option to filter fragments actual replacement will occur or generation. In this, for this, we implemented a specific way how to alter this using filter functions, and users can implement their own filter functions. Here I just show an example how these functions may look like and their idea. So if you are interested, you can read the documentation and then try to implement. If not, you can ask me if it will be necessary and I will help you with that. So the idea is that, yeah, there is a fixed interface of those functions. First 3 arguments are always the same. And then there are some user-defined arguments can be. For example, in this case is the atom number. And the idea of this function, we want to keep only fragments having a particular type of atom. So we want, for example, to make replacements with fragments having, for example, hydrogen, chlorine, or bromine, or fluorine. Actually, fluorine can be quite useful because sometimes you need to generate compounds, create structures with fluorine in their structures to be available for NMR experiments, to measure the binding affinity, for example, in NMR. Here I will not stop in very much details about this function, just briefly. So it returns you should return the whole list of fragments which can be used for replacements and then perform filtering based on the atom number, in this case, and return back the IDs of those smiles which we want to keep to make a replacement. And we can apply this filter function to the linking option. So we again link the same 2 molecules. And we want again link the same atoms in them. Distance 4. In this case, we specify the size of atoms from 5 to 15. And we pass another argument, which is a filter func. And we pass this as a function, as a partial function, where we predefine the argument atom number equal to 9, which is corresponds to fluorine. So in this case, we want to generate linkers which contain at least 1 fluorine atom and have from 5 to 15 heavy atoms. Oops. I didn't execute, first I have to execute function to become available. And then we will see just 4 structures. And all these 4 structures, they have a distance between fragments connected, 4 bonds of 3 atoms, and at least 1 fluorine atoms, here 3 atoms, will be in each of these generated structures, and in each of these added fragments. So this is a more advanced level, just to be aware that this functionality is available. So if you want to tweak it, again, if you can post-process and you can filter output structures based on this rule and get the same result. But if you need something complex, if you need to do this programmatically, here is the way how to do that. And this avoids excessive generation, because otherwise, if you will specify these settings without filter function, it will return you really a lot of structures. So we can try to do this. Probably there will be something like thousands and thousands of molecules. So we remove the filter func. Okay. And let's see. No, just 88. So our other settings were quite restrictive. So not that many compounds were generated at all with these settings. But normally, it may happen that it can generate thousands, and it can take some seconds up to minutes. That it may be not desirable if you want to create some fast application.
And is there any other disadvantages of doing that? Like, it's not a good practice that I over generate too many structures and filter it afterwards. But like streaming the file system, or it's really like undemanding, so I can do it even though it's not like a good practice. Like any technical issue.
I didn't understand the point. What
No,
is?
but if I do like generate thousands of structures
Yeah.
and then filter them,
Yeah.
so you said it's gonna be fast, even that like
It,
like
it may. Yeah.
But is there like any other disadvantage, like technical one?
No. 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 No.
Okay.
So you will receive those molecules. It will be in this list. You will just need to find them. So.
Yeah.
But yeah, for our tasks, even few minutes we consider quite long. So
I'm an MD person, so
yeah, I understand that in some fields it's not so relevant, but if you want to generate millions of structures, 1 second, 1 minute, it's already something considerable. But yeah, if you just generate once, yeah, you can generate everything and then just try to find what is relevant, what is not. Yeah, you can also specify the max replacements argument. If you don't need to make all replacements, but you can be satisfied with some random subset of possible replacements, you can specify this argument, in this case 2. So we execute the previous linking example, and we specify max replacement 2, and it will return just 2 out of 4 possible replacements. And it will be done completely randomly. So here you see, okay, we have 2 structures with fluorine in a linker. We run the code once more and we got the same structures. Okay, once more, again the same. No, it is not possible. It is. No. So yeah, it's just randomness. So I reproduce several times the same output. But normally it select randomly those replacements and return to you. And unfortunately, this is another issue of unsolved issue of CReM, since there are not so much demands for that. These replacements randomly chosen are not reproducible. So you cannot specify seed in the beginning to make all these random choices reproducible. So each time they will be completely random. So you won't be able to reproduce this random choice. It's no. If you ask all replacements, it will return us all possible replacements. But if we specify max replacements less than maximum possible one, then it will return us just a subset of molecules which will be random, and we will not be able to reproduce if we will run this function the second time. So you may reproduce like me 5 times in a row, but normally it will not be reproducible. And the last advanced functions is the sampling functions. It's similar to filtering functions, but filtering functions makes strict decisions. So yes or no, which structures we want to keep. Filtering functions works a little bit. Sampling functions works a little bit in other way. So in this case, you modify the random selection of fragments, because by default, if you ask to return you some maximum number of replacement, for example 5, it just uniformly picking those structures, those fragments from the whole database. For example, you have 1000 possible substitutions, replacements, and you ask just 5, and it will uniformly choose random these fragments. But in some cases, for example, you want to create a bias in the selection of fragments. And in this case, you can implement such a function. For example, for our studies, it was quite useful to make a bias based on the number of saturated carbon atoms. And we wanted to preferably randomly select fragments, but preferably more saturated fragments, having more saturated atoms. And for this reason, we could implement, and as a user, you can also implement your own sampling function if you have some other idea what you want to do. And again, it has a fixed interface. So 4 input arguments, row IDs, cursor, database cursor, radius, and number of fragments to be returned. And then you implement your logic. So based on row IDs, you can return from database the smiles of structures. Then you can calculate some particular descriptors, parameters, and then you can create probabilities based on these values of parameters. In this case, it was the number of saturated carbon atoms. And then you can apply standard Python functions to picking fragments from this long list proportionally to probabilities which you computed within this function, and return back row IDs of those fragments which you want to replace actually. Yeah, this logic could be looking quite complex, but if you will need it, it will be quite easy to implement. Again, in documentation, in README, in the repository, there are some examples. So we can execute it, and again, we can add this sample function through additional argument, sample func. So in this case, it will just randomly choose one fragment which should have, with a higher probability, more CsP3 atoms. And you can see that, yes, this fragment has 3 saturated carbon atoms, while if you look on those 4 possible structures, only one have many saturated carbon atom. This 1 carbon atom saturated, this 0, this is also 0, and this is 3. So probability works. So we could, of course, it will not work always. Yeah, in some cases, it can return you fully aromatic structure. But if you run this multiple times, based on the statistics, it will work. Yeah, some functions are already integrated in CReM, and we can expand it later as well. And if you have some ideas what can be useful, you can contribute. You can ask me to add to the repository and to the module. So we are still working on this and continue to develop this approach, this module, support it. And yeah, I hope that it may be useful for your work, because yeah, it's very simple and it generates some quite reasonable suggestions. This is not the end, so I'm just wanted to ask, do you have some questions regarding this part of the presentation? How to modify, maybe you have some specific questions, some needs, maybe you have some ideas how to apply this, and you have a question how I can apply to my task. We have just 15 minutes before the finish, so maybe we will not start the next programs. I will just show you what can be done next. If you are interested, you can execute those commands from the tutorial files and apply and generate structures de novo, because on top of CReM, we develop and still support and develop some tools which generate structures to address different practical tasks. And currently what we have generation based on 3D pharmacophores or guided by molecular docking. So if you have a pharmacophore model, you can use this model to guide generation of 3D structure satisfying exactly the geometry of a pharmacophore. Or if you have a binding site, the protein structure, you can use CReM dock to generate structures within the docked binding site with the highest or high docking scores. Or you can use the same, if you have a binding site and you have your ligand, you can optimize the structure using mutation, automatic mutation, and guide it again by docking scores. So these address different questions like de novo design, heat generation, lead optimization, scaffold hopping. And these outputs can be used to searching for active compounds. If I will have time, I will show you an example. Just briefly to show you how it may work, for example, for generation with pharmacophores. Yeah, these are the known complex of a ligand with its protein. These are CDK2 protein. We can, as Thierry showed you, annotate with the pharmacophore features contacts which are observed in a complex. These red spheres are acceptors, green donors. These one are aromatic or hydrophobic features. And then we populate with exclusion volumes to create something like virtual binding site, wall of the binding site, to avoid proliferation of a ligand in directions which are not desirable and occupied by protein atoms. So we put exclusion volumes to all protein atoms around this binding site. And then for clarity, we hide these exclusion volumes, but during the generation they exist. Then we, of course, remove the initial structure, and then the algorithm is very simple, and that's why it's pretty fast. It can be even faster. We are currently working on an extremely fast algorithm, but even now it's pretty fast. So we select a user specify, okay, which features can be used as a starting point for generation. For example, a user can select those 3 features which defines the hinge region binding motif. So 2 donors, 1 acceptor. And it performs screening. And for example, okay, some fragment was found. And this fragment was already aligned with the pharmacophore features. That's important because on the next step, we select those fragments and we try to grow them in the direction of the next group of pharmacophore features, the closest one. For example, in this direction. And since this starting fragment is already pre-aligned, we don't need to perform pharmacophore alignment of the generated structure. So we generate substituents in different positions and just generate conformers only for the substituent and check does it match those features or not match, like this one. So we generate conformer only for this substituent, and yeah, in this case it could match both hydrophobic features, and we keep it. Again, fix the conformation. And I also would like to recommend you this CDP kit toolkit, which advertised by Thierry Langer in his presentation, because they have really very fast, ultra fast conformer generator. Yeah, the same stuff can be done with RDKit, and CReM Farm supports several conformational engines like OpenBubble, RDKit, and CDP-Kit. But in our experience, CDP-Kit is something like 90, 100 times faster than RDKit. So it's really substantial. And due to the CDP-Kit, the generation is really fast. But it can be even faster because we generate a lot of structures, enumerate those conformers, it nevertheless takes some time. But with CDP kit, this is already something very feasible. So you can explore much larger chemical spaces. You can generate much more compounds. And on the second step, on the next step, again, you just try to attach to existing molecule another fragment which will match another remaining features. And this procedure is iteratively called up until we match all features or compound reach the maximum molecular weight, because we always restrict the generation by molecular weight, by the size, by other properties like lipophilicity, some other physicochemical properties. And that's very simple. So you get a molecule with a conformation which satisfy your pharmacophore. So it's not like in some, there are quite currently, so already some approaches exist where a compound is generated by neural network based on the pharmacophore features submitted to it, but it doesn't guarantee that the generated molecule will be able to match these features in 3D. So those compounds will contain those features, but the placement and geometry of a molecule does not guarantee. So when you generate those structures, you need to filter them based on the pharmacophore, and the number of these compounds will really reduce substantially. So in this case, we explicitly generate molecules which can satisfy a pharmacophore model. Yeah, and another quite interesting note that we also try to avoid excessive decoration. So that's why it means on each step, we remain only compounds which have the minimum number of atoms matching the maximum number of features. For example, if we have two compounds, one have a phenyl substituent, another one have a toluene substituent, and both of them match the same pharmacophore features, we will keep only one compound having the phenyl substituent, because phenyl is a substructure of toluene. And it means that this additional methyl group is not relevant to match pharmacophore. And if it will be needed later, the program probably will find this methyl. If it doesn't need it, we do not generate. So we avoid excessive generation, and in this case, we generate the minimum possible structures which satisfy the pharmacophore, a given pharmacophore. So that's why we generate not that many compounds. But if necessary, you can decorate it further. You can add some halogens, methyl groups, some methoxy groups if needed, whatever. So we generate like frameworks which can be further grown if necessary. And also it was designed in such a way, so we try to generate molecules in a way to balance between exploitation and exploration, and generation can be interrupted at any point and continue from the any point. So if your generation just interrupted, or you can stop it by yourself, then you can just call the same command and it will continue from the point where it stopped, because it may be not necessary to explore the whole number of compounds. You can just generate first 100 and interrupt the generation. But later you can want to continue, for example, search. Here are just examples of how yeah.
Like available.
Yes, all these tools are available. CReM Farm, CReM Doc, all these tools are available. The links are in the tutorial materials. They are open source, so you can install them using the same environment. They are also installed on your computer, so you can even try from your computer right now if you have a pharmacophore model. So we are short in time, so that's why I'm not pushing you, but if you are interested, I can show you how it works. But yeah, these are open source, and you can find links to repositories. And we always supplement with examples. So in README, you can find examples how to run it. You can find them in tutorial materials as well. So you can download those.
So that's basically also create from model.
No. You should create it by yourself.
Yeah.
So it's completely up to you how to create it, ligand-based, structure-based. Currently, the format is very simple. So you should submit file in the XYZ format where you have the coordinates of each feature and type of each feature. And type of each feature encoded with one letter, single letter. You can read how it is encoded, and that's all. It does not support currently the directed features like hydrogen bond donor acceptors. It just will consider them as undirected. So this could be a limitation also. But if you have a structure-based pharmacophore from the protein, you create these exclusion volumes. That's also quite useful. So you put to each protein atom the center of exclusion volume, and you add to this XYZ file exclusion volumes. This can be 200, 300 exclusion volumes, doesn't matter. So it's good to select quite far away atoms to avoid some holes between these exclusion volumes. Otherwise, ligand can proliferate through these small holes, and then the structure will not be relevant. So it will explore some not relevant chemical space. Just the last maybe example that, okay, we can generate structures using different settings with a pharmacophore. So here we vary the fragment database from the full to the most restricted one, and using different radiuses from the smallest to the largest. Then we select top. Then we dock all those compounds, selected top compounds based on the docking scores, and calculate for these top 100 compounds assay scores. And you can see here is a trade-off between docking scores of the designed compounds and their synthetic accessibility. And these points, they create quite clear Pareto front. So you cannot generate compounds which have excellent docking scores and excellent synthetic accessibility, but you have opportunity to predictably change the synthetic accessibility and docking scores for compounds. For example, for radius 5, you go from full database, medium database, and small fragment database. The same for radius 4, full, medium, small, full, medium, small. So in all cases, you can find a compromise between the docking scores and synthetic accessibility, just tweaking these parameters. And the same happens if you analyze them from the point of view of the chemical databases. For example, we can take this one, this one, this one, then this one, no. Yeah. These are radiuses and databases. Yeah, I have taken. Yeah, these are the same radiuses, the same databases by those ones. So green, yeah, this one. So they also change in the same direction. So we have small radius, like 1, 2. We got good compounds with excellent docking scores, but they're overly complex. If we change the radius, we will improve synthetic accessibility, but may worsen docking. Docking scores per se, they are not the ideal objective function, but it can be still useful. But it doesn't mean that, okay, my compound is not -11, but just -10. It's not enough. It is bad. Doesn't matter. It can still be useful for your project. Docking scores is not that much sensitive. So that's why you may consider it, even such compounds. So you may consider still quite restrictive settings for generation of structures. to generate molecules. Yeah, I have a lot of more examples for you, but I'm not sure that you are ready to digest all these examples. But if you want, I can continue. Or if you want to just stop, we can stop the discussion. I can show you just examples from practical exercises. So it's up to you. If you are hurry up for trains or I don't know, dinner, okay, so okay, I will continue. If you need to already leave, so you can leave. No problems with that. So at least you're already aware about this approach. You may try to use it using the web-based application of Python. If you will have any further questions, you can ask me now or then by email, for example, or in GitHub issues if needed. Okay, so if there are no reactions, so then I will continue. Sorry. I will just discuss and show you some examples without some coding. If you want to run some examples, you can find the examples in the tutorial PDF file and just try to execute those commands. Here is just examples of compounds which were designed using the pharmacophore. So here's the reference compound with this pharmacophore, and here's the compound which was designed with a higher number of saturated atoms. So maybe it would be active, maybe. So it looks like it could be bind to the hinge region. It satisfies some other pharmacophore points. So CReM doc is another our development, which is pretty much standard, classical, I would say. So this is the iterative growing algorithm. So we start the generation from fragments taken from the CReM database. So first, of course, we molecules. Most frequently for our studies, we use CReM database, but not necessary. So we create fragments using the CReM. Then we select some starting fragments, dock them to the protein. This docking is supported by EasyDock, as I told you. So we develop some ecosystem of tools which would address different questions. And in this case, EasyDock is really easy to integrate to Python programs to support docking. So we use docking of these fragments. Then we select most favorable fragments for the next iteration. There are several strategies how to select them. We can make a greedy search. So we select fragments with the best docking scores, for example, or we can try to select diverse set of compounds. In this case, we cluster those fragments and then picking from the individual clusters representative structures. Or we can use Pareto selection, for example, finding the best balance between the docking scores and molecular mass, trying to discover the compounds having the best docking scores and the lowest molecular mass. And then selected compounds, they go to the growing with CReM, and then we perform filtering by physicochemical properties. To avoid generation too large compounds, we restrict them by the molecular weight. Additionally, we restrict by lipophilicity, can restrict by number of rotatable bonds, because sometimes it's more preferable to generate more rigid compounds. Because if more rigid compound is satisfied, again, it's very much relevant to those you learned during this workshop, that more rigid compound, if they satisfy the protein contacts, may be more favorable for interaction because you lose less degrees of freedom. So we restrict by physicochemical properties, and this cycle repeats several times until we get molecules with a large enough structure. And those hits we select and analyze as outputs. Additionally, we can control not only physicochemical properties, we can control protein-ligand interactions, which is also quite important because, for example, if you design compounds and you know already about some important interaction, it's not reasonable to randomly generate compounds without considering this important information, because afterwards you will post-analyze and you will remove those compounds which do not interact with a particular amino acids. In this case, you can specify in a specific format which contacts should be kept with a protein, and those molecules will be preferably selected on each iteration, and in this way the output database will be populated with a much higher percentages of compounds satisfying those protein ligand interactions. This was done through the ProLeaf library. Yeah, and we also have features to keep the pose, something like constrained docking. The example of our studies are pretty much the same, the output, so we perform multiple studies, and again we observe the same trade-off between docking score, assay score, and again we observed quite controllable change in docking scores and synthetic accessibility scores depending on the radius and the fragment database. Augmentation, yeah, we can bias by enrich generated structures with saturated carbon atoms, as we use this specific sampling function, for example. That's possible. Here is just demonstration that wait, see you. So here just example, if we have the same protein, these are 4 proteins, these are all CDK2, and we took different proteins, we ran generation, and we got different results. These are just to point out that we do not now consider the scores. Yes, scores can differ, but scores are not that important. It just demonstrates you mainly 2 things. The first one is that for different structures, the synthetic accessibility score is almost the same. So it's in the same range of values for top scoring compounds. So it's not so sensitive to the structure, the complexity, synthetic complexity of the design compounds. It's sensitive only to the settings, the radius and the fragment database. And also the structure are quite diverse, generated for different protein structures. These structures, they started from the same starting fragments, but they grow to completely different structures afterwards. And here you can see that, yeah, here we count the number of common scaffolds across different generations, and you can see that even for the same protein, there are not so often even overlapping scaffolds, the same scaffolds. So these are another example that you can run this generation multiple times and you can get different chemical space. You can get different output structures. Yeah, because we do not make exhaustive enumeration of compounds on each iteration. So we usually enumerate just up to 1,000, maybe 2,000 maximum of possible structures for each parent compound, because otherwise this generation will be really large. So it can generate dozens of thousand structures, which docking will be prohibitively expensive. It could take weeks already. Yeah, here is this comparison how designed compounds can be compared with randomly selected compounds from zinc. So if we select the same number of compounds as we generate from zinc and dock them, select, and the best compound of zinc will be quite far away from those best generated structures. So it just demonstrates you that when you explicitly bias your generation by docking score, you can achieve really high values comparative to just random screening like traditionally, using the same computational power. So we make the same docking events in all these experiments. Here is another example of how we can perform fragment expansion. So we selected from PDB database several examples where we have compounds, pairs of compounds, some smaller one and larger one, which differ in their activity, affinity values, so micromolar, nanomolar affinity. And then we ask our algorithm, CReMDoc, to grow these structures in order maybe to find the desired compounds, but generation was guided by docking, and it's not necessary to reconstruct the same structure, because those structures may have quite bad docking scores, for example. In this case, the algorithm may not find it, exactly this structure. In one case, we could reproduce exactly the same structure, yeah. This also similarity is 1 because it's a just larger ring, so 7-member ring system. Instead of 6-member, it has the same fingerprint, and that's why the similarity is identical. But in other cases, yeah, we could not achieve exactly the same structures, but we just demonstrate that the generation went in the right direction. So they could generate additionally substituents. For example, in this case, they started from this structure, they added this amino group, this benzyl oxy group, to find quite important interactions. Yeah, unfortunately, in this case, they couldn't generate this positively charged nitrogen. Yeah, it could not select these structures on some intermediate steps, so that's why it couldn't be reached. In this case, yeah, again, we grow this molecule. It could add this part, but instead of a cyclopentyl, it could just add a methyl group. So didn't go further for some reason. And the reason is that here is the 3D structures. The reason is that this cyclopentyl group, it looks somewhat outside already of a binding pocket, and that's why docking cannot understand the importance of this group already. So that's why it was not generated. But it could reproduce another one. So just examples. Here is just comparison between two programs, CReMDoc, CReMFarm. Gray dots are reference Campbell space. These are known actives of CDK2 from Campbell. The red ones are generated by CReMDoc, top scored molecules. Green ones are generated by CReMFarm. And you may see that they not overlap with each other. So each tool generates something different. In this case, CReMFarm better overlap with the known chemical space, but still it generates novel compound. When we calculate the similarity between the known structures and the generated ones, the similarity was always very low. So below 0.4 usually. Again, it depends on your settings. Yeah, the larger radius you will choose, the more conservative replacements will occur, the more close those compounds will be to the known structures. So this is also the possibility to generate and control novelty. Here is one example how we tried to apply this many years ago. So we had such a structure. I cannot show the scaffold, but scaffold is the same in all cases. And our chemist found that, okay, this compound is highly active. It's selective towards normal cell lines. So these are cytotoxicity towards different cancer cell lines. And they were interested to develop it further, to design compounds which will have better solubility, will be less lipophilic, and keep the same level of activity. So they asked us to generate some structures. So we enumerate and docked many compounds, and then we just plot them, lipophilicity, docking scores, and select those compounds which were in this region. Here is the lead compound, this one, where it is placed according to the docking scores and the lipophilicity. So they wanted to be below 4. It's the ideal case, but we couldn't find this compound because the scaffold is quite lipophilic. So the baseline was already quite high, but we tried to even reduce this lipophilicity. And we generated some suggestions. And once one structure was already synthesized, tested, and unfortunately, yeah, the activity decreased. Yeah, it's still active. It's still selective, but the activity is considered as quite moderate. Not low, but moderate. So it's micromole.
So that's just some paclitaxel analogs to be better soluble in something else.
These are analogs, I would say, not paclitaxel, colchicine, but yeah. So this was an idea trying to target this binding site, and this binding site is quite lipophilic. There are almost no hydrogen bond donor acceptors inside, so that's why the scaffold is very specific to satisfy these few contacts. And this substituent just looking and fills the cavity, which is also quite hydrophobic, but maybe some other compound will be more active. Additionally, to those compounds which were enumerated and suggested, the algorithm also generated some compounds which were previously also designed by chemists and synthesized, but without our recommendations. And those compounds were quite active. So in theory, if chemists had just this starting molecule, we could rediscover all these ones as well with CReM. So we could generate them, dock. They were also satisfy this criteria, and we could get them. But this is not fully successful story, I would say. But at least this shows some promises that, okay, this may be reasonable. These are the large example. What we did in the first cache challenge. To those of you who not aware about cache challenges, these are prospective challenges for leading chemoinformatics groups all over the world, where groups try to find active molecules which are prospectively validated by organizers. So you really submit structures which will be biologically tested, and you can evaluate your tools, your pipelines in this way. And for the first challenge, the task was to find binders of this specific domain of a kinase which is relevant to the Parkinson disease. And the complexity was a twofold, because the first one is that there were no known binder of this specific domain. And this specific domain looks like, I don't know, donut. And they expected to target this central cavity to find some molecules which can bind inside and use them to design PROTAC compounds to degrade this kinase. Another complexity and challenge came from the chemical space, because they were organizers asked us to select compounds from the enamine accessible chemical space, which was at that time about 20 billion structures. And that's also quite challenging, because you cannot dock all of them. So you need to create some smart approach how to find these needles in this haystack. And we didn't use pharmacophores in this case, as Thierry showed. So we used, as a major idea, was that we can generate de novo structures which can fit to this particular pocket. And then we can use these structures as a templates to find the active compounds by similarity search in this virtual library. Because similarity search is extremely fast, and it can be performed for billions of compounds in minutes. But since there were no known ligands, we can just generate them. Yeah, they will be quite artificial. They may be quite artificial. But they can be used, it's like a fishing. So you create some, I don't know, nаживка. Yeah, how it will be in bait. Yeah. We can create a bait, de novo generate, then push to our pond with all structures, and then some structures will be similar, and then we will find something in this way. So we generated structures de novo using mainly a growing algorithm. Further, one more thing that we used in this case enamine fragments, because we expected that those molecules which we designed would be possible to synthesize. And organizers, they covered the synthesis of compounds. That's quite nice. And we expected that they will be really synthesizable.
But you know the target.
Yeah, target was, and we had the crystal structure of a protein, but no complexes and no structures of ligands, reference ligands. Here is the whole workflow. It's quite complex because we knew nothing about this structure, about this protein, about this task. So that's why we investigated flexibility using MD. And this was also initiate us to develop this StreamMD tool, which was presented on this workshop. Then we took from different simulations representative protein structures. So 4 protein structures were taken. We generate ligands de novo. We got 4 hit lists. Then we tried to optimize those structures using the genetic algorithm. And then we combined all output structures in one pool, filter them by docking score, physicochemical properties suggested by organizers. So there were some requirements for ligands, and then perform consensus docking. So we select top scoring compounds and perform docking by different programs in all 4 protein targets. And we got 16 lists as outputs. And then we perform exponential consensus ranking of those 16 hit lists altogether to find 200 most promising compounds. And then based on the consensus post-selection, we perform very short MD simulations to rescore the final set of molecules and select 50 compounds at this stage. And these compounds, 50 compounds, here are just some examples of those designed molecules. For some of them, we could recreate the synthetic, retrosynthetic pathways, so they might be synthesizable according to the Eisenfinder predictions. And we submitted them partial as a one batch of compounds. The second step of the first round of design, so we took enamine real space. We used F3s, as this is approach from Biosol YT, which use for similarity search pharmacophore-like representation in 2D. It's extremely fast, extremely efficient. For each query compound, we got 1,500 structures. We again combine all these lists together. There were some duplicates, of course, also retrieved, filtered them by molecular mass, other physicochemical properties, then again perform consensus scoring, selection, rescoring with GBCA based on just 1 nanosecond MD simulation. It's extremely small, but we couldn't run longer because the whole stage was limited to 2 months. So we have to deliver those compounds in 2 months, those predictions. So that's why we are quite limited. Finally, we remove compounds having pains. We remove compounds having no polar contacts in the binding site during the MD simulations. And we submitted for purchase those 50 de novo design compounds, these 100 compounds selected by similarity based on the pharmacophore representation with F3s. Within the budget, we selected 91 compounds because organizers asked us to select within these budget structures. 82 of them were synthesized and 8 of them were active. So they could bind to some extent. Yeah, you can be surprised by these numbers. So these are micromolar, something like lower micromolar affinity. But the target is really complex, and I would say that the best ligand after all stages across all groups had something like 15 micromoles. So it's really complex to target this protein. Yeah, at the second stage, they asked us to optimize those structures to find some more potent compound, and we based our search on this substructure which occur in multiple our active molecules. So we tried to enumerate in different ways, again perform consensus screening, whatever, and we designed several compounds which were further submitted at the second stage, again experimentally validated, and one compound were evaluated as a good one, again quite moderate affinity, but it was a real binder, because there are a lot of compounds which were suggested, they weren't bind to the target. And with this result, we possessed the third place in this challenge, which is quite nice. Nowadays, this challenge already not fully covered by organizers, so participants should pay for synthesis of those compounds, and that's why me and my group do not participate in this challenge anymore. But it is still quite interesting. So if you have some funds, you can use this challenge to test your skills, your pipelines, approaches. And what is important in all this pipeline, which we designed, that there were no human selection. So all steps were purely guided by predictions. So we didn't make manual selections like all other groups. And we were the only group who did not make some manual selection of structures. So we just blindly sent what computers predict should be active. Maybe we were lucky, maybe not. Currently, we perform larger studies to more systematically explore conditions, settings, different settings, how they may influence the output for this strategy when we generate de novo templates and use them for finding active molecules by similarity search. So yeah, that's all what I wanted to show you today. I hope that you are not too tired. Yeah, I'm almost half an hour later. So just to show that, yeah, some summary, you can look on it. So I hope that you will see during this tutorial that this tool is quite flexible. It can really address a lot of tasks. You can really make what you want with the structure in a very predictable way. There are a lot of databases which we already pre-generated. They are available by the link to the nodo repository provided in tutorial materials. So you can use it. You can find the old Campbell databases, new Campbell databases, Yanamin databases, and you can choose what you want. So here I just look on the recent statistics on downloads. So it's still quite popular. Sometimes it's higher, sometimes it's lower, but the number of downloads roughly 4,000 or 5,000 per month. So it means that this is really something useful, something useful. So it's, yes, here are some links on our software which we develop. Yeah, this already publicly available. So I didn't update the slides. So all these tools are already available. So you can find them in our GitHub repository, all of them. Here are some references for future of these tools. Here is the team which contributed to the development of all these tools, because it's impossible to make alone all this stuff. And that's all. So thank you for your attention, for those of you who survived. So if you have some questions, you can ask.
Yeah, I was thinking, would we like implement a de novo generation and then create like a data set of for active learning methods, and then to screen ultra large libraries, or similarity search is still way faster?
I'm just thinking, what do you mean active learning?
We create like
You mean create de novo
yeah, from the
structured de novo design using active learning, or
or maybe I'm missing some
Uh,
of the information. So we generate the structures, and then we use this as the say like the data set, and then implement active learning to screen billions of components.
You mean we can build a QSAR model which predict docking scores based on these structures, or what do you mean active learning in this case? Could you specify more precisely? Because I cannot catch
Maybe
the idea.
the active learning method is the method when we instead of screening and docking like billions of compounds or hundreds of millions, we take the small percentage, let's say 1% or even 0.1%, and then we train the model on this percentage.
But train which model? What it predicts?
Sorry,
No, we really train the model, but what it predicts in your
and then
opinion? In active learning, it normally predicts docking scores. This is how deep docking works, suggested by Cherkasov many years ago. So they take subset of large library, dock it, get these docking scores, build simple QSAR model, predict the rest of the library, again select the subset of molecules, dock them, combine this set in a single one, retrain the model, and after several iterations, they can quite well predict the docking scores for the rest of molecules. This is active learning implemented by Cherkasov, for example. In this case, it may be possible, but I'm not sure that it would be relevant because the chemical space generated by de novo and those libraries may be very different. The similarity, actually, we checked the similarity of structures in Cache Challenge, which we submitted for similarity search. They were quite different. Yeah, in the pharmacophore perspective, they were quite similar. So similarity was almost above 0.9. But in the structure similarity, it was below 0.4. So it means that there were no common patterns.
No. The longest need more participants than
We attract next time maybe more viewers, more money from advertisements. I don't know. Maybe we'll be able to pay for coffee breaks next time. I don't know. So they're quite dissimilar. So those structures, even if you will use the fragments from enamine, it doesn't mean that we can quite nicely reconstruct the same chemical space. Because enamine, even real chemical space, yeah, it's large, but it's nothing relatively to the whole chemical space available. And that's why even this billions compound, it's almost drop in the ocean. And when we generate de novo, we try to cover the whole ocean. That's why we can go in any direction, and it doesn't mean that we will go in this exact direction of real space. So yeah, this number is really enormous, but we shouldn't forget the real chemical space is orders of magnitudes larger. So that's why maybe this active learning based on the docking scores maybe not the best way. But you can invent something interesting. Why not? So think, or continue thinking. Why not? So any guesses? Any guesses?
maybe one more.
Yeah, sure.
From the like generated from the generation mutation, can we set the like pharmacophore parameters for those generated to maybe like speed up the generation process, or it's still like a random generation? So, for example, we from the molecule we choose like 8 heavy atom positions, then we generate in any direction. Can we set some like parameters that the generated structure will have like some pharmacophoric features that are interested?
Yes. This can be achieved. No. It is possible. I didn't show you during this presentation because I thought that it will be too advanced already. But CReM is designed in such a way that you can additionally annotate fragments in a database with any properties you want. So you can annotate fragments. There are some already predefined scripts, and you can predefine and you can annotate them based on the number of pharmacophore features of different types, for example. That okay, I have in this fragment 2 acceptor, 1 donor, nothing else. And these will be separate columns in a database, and they can be used to select fragments for replacement. So you can specify, okay, I want to find fragments having particular features. And then it is possible. I can show you. It's because all these databases which are available on Zenodo, they already annotated with these additional properties. They annotated with physicochemical properties like molecular mass or number of rotatable bonds. So you can control even this. So if you want to make replacement and you want to have fragment with 5 rotatable bonds, you can just specify this and it will return you only fragments with 5 rotatable bonds as a replacement. And the same for pharmacophores. And there is additional customized features. I will open the just database to show you how it looks like. So yeah, here is the database. There are multiple tables, but they're the same. All radiuses look the same. So environment, smiles, size of a fragment, smarts, distance, and then those populated properties, molecular mass, lipophilicity, number of rotatable bonds, whatever. And all these additional columns can be used as arguments in functions. And if you go back, let's take some well-populated example where we have many structures like this one. Okay. Now we can make it in place, for example, just this. And here you can, okay, I want to have number of acceptors within from 2 to 3 in a fragment which will replace my fragment. No. Never closed. Okay. And instead of 2,100, you will get just 1,000 compounds. And if you draw them, you will see, okay, it adds fragment 2 acceptors. 1, 2 acceptors. 1, 2 acceptors. These are acceptor and donor. No, this is only donor, so 2 acceptors. But there should be, here is a donor. Actually, yeah, it disregards the environment, so this atom is annotated as acceptor because it's amine, but depending on the attachment, it changed. So yeah, here you can find this, and you can use, instead of number of acceptors, molecular weight, for example, you can use some molecular weight equal, I don't know, exactly 300, but it will be 0, of course. It's not relevant. So from 200 to 210, for example. And you will get these results. You can combine them all together. So you can combine them molecular mass with number of acceptors. For example, 2 from 3. It is still there. So there are some suggestions. So it's quite flexible. There are a lot of flexibility inside. So it was designed in such a way that you can extend it further. Now we are working on optimization of the database structure to make it more compact, to reduce the size because there are a lot of duplicated information stored. Yeah, it will maybe a little bit slower the generation procedure, but it will really reduce the size up to maybe 10 times. So 5, 10 times, because these databases, for full fragment databases, they can be very large, like 100 gigabytes. It's quite easy. But even with 100 gigabytes, it works very fast, because database is currently denormalized and it's very fast. When we will normalize them, they will be smaller, but maybe slower. So we will test this. Yeah, this is like a hidden feature. It's not hidden, so it's also described in README. I just didn't want to go into too much details. Yeah, it's still evolve, so it's still evolve. Maybe we'll implement something new. I already have some ideas how to create CReM 2.0 version with completely other idea behind, which should be faster and more reasonable, more applicable. But it's a matter of future. So some other questions? Oh, everybody tired. Me as well, but what to do? This is a workshop. So thank you, and maybe see you tomorrow, if you will survive till tomorrow and will come for the challenge. I will prepare this challenge during tonight, and I will be ready for tomorrow. Yeah, thank you.